Hello there, and welcome once again to Science for Sleep, where curiosity gets cozy and science takes its time. Tonight we turn our attention away from the familiar glow of our own moon and drift far across the solar system to a place that doesn't hum with calmness but with constant upheaval. Out there, orbiting the giant world of Jupiter, lies a small moon that seems to live in permanent turmoil. Its surface is cracked, scorched, reshaped again and again, not by the slow hand of erosion but by eruptions that roar upward with more power than anything we've seen on Earth. This is Io, and though it may be a world of rock and ice like many other moons, it has earned a reputation as the most violent body in the solar system. When you look up at the night sky, you see steady pinpoints of light. They seem so tranquil, so permanent. Even when you know each one is a star or a planet racing through space, the view from Earth is still calm. That makes it almost impossible to imagine a moon where calmness doesn't last. Io is the opposite of peaceful. It is a world where fire breaks through the crust again and again. Volcanoes spread fountains of molten sulfur dozens of kilometers into the sky. Entire regions are paved over with new lava flows in a matter of weeks or months. And yet, despite all this chaos, Io is strangely beautiful. Covered in yellows, oranges and reds, its surface looks like an artist's palette spilled across stone. Before we step closer, let me ask you something. Have you ever had a moment where you felt pulled in two directions at once, stretched between choices, like forces outside of you are shaping the outcome whether you wanted them to or not? Io lives that kind of life constantly. Trapped in a tug-of-war between Jupiter's immense gravity and the pull of its fellow moons, it is stretched and squeezed until the very rock inside heats and melts. This endless struggle is what powers the eruptions, what makes Io unique among all the other moons. And as we take our time tonight, moving slowly through its story, I hope you'll find it soothing in its own strange way. If this journey helps you unwind, if you enjoy wandering through science at this calmer pace, I'd be so grateful if you gave this video a like or perhaps subscribed. That way others who might be looking for a moment of rest can find their way here too. Now let's settle in. Loosen your thoughts as though you're reclining into a comfortable chair. Imagine the vastness of space stretching out beyond our planet, beyond the orbit of Mars, beyond the cold realm where Jupiter dominates, and somewhere there in the shadow of that giant world is a tiny glowing bead. That bead is Io. The story of Io is not a quick one. It is as restless as the surface of the moon itself, and so we begin, gently, with the very first time humans ever looked at it through a telescope. Io was first seen clearly by Galileo Galilei in January of 1610. He had built a telescope more powerful than anything before, and when he turned it to Jupiter, he noticed something remarkable. Not one, but several tiny points of light hovered close by, shifting from night to night. At first, he thought they might be stars, but soon it became clear. These were moons orbiting Jupiter, 4 in total, which we now call the Galilean moons. Io was one of them. For Galileo, this was more than a discovery of new worlds. It was a revelation. Until then, people believed that everything in the heavens revolved around the Earth. But here was evidence that not all things did. These little moons circled Jupiter, not us. Imagine Galileo's excitement, and perhaps his unease as he sketched their positions. Each night Io moved, sometimes appearing to the left of Jupiter, sometimes to the right. It was the first time humanity realized there were other miniature systems out there, like tiny solar systems orbiting a planet instead of the sun. Io was already playing a role in reshaping human understanding, long before anyone knew what it truly was like. Through those early telescopes, Io appeared as a small point, nothing more. For centuries that was all anyone could see. Even with improved instruments, its disk was too tiny to reveal detail. It wasn't until the space age that Io gave up its secrets. The Voyager spacecraft in the late 1970s were the first to fly past and capture images in detail. What they revealed shocked scientists. Instead of a cratered, icy surface like most moons, Io looked young and fresh, scarred not by impacts but by volcanoes. Bright plumes towered above its horizon. Dark patches showed fresh lava flows. Voyager had stumbled onto the most volcanically active body in the solar system. If you were floating above Io during one of those eruptions, you would see fountains of molten material reaching hundreds of kilometers high. They arc back down, painting the surface with new deposits. Some eruptions are so energetic that material escapes Io entirely and joins a vast cloud around Jupiter. The moon is literally bleeding into space, feeding its environment with sulfur and other particles. From afar, Io's contribution creates a torus, a ring-shaped cloud that circles Jupiter, glowing faintly in ultraviolet light. In this way, Io doesn't just change itself, it reshapes the space around its giant planet. But what drives this incredible violence? The answer lies deep beneath the surface, and in the constant pull of Jupiter itself. Io is locked in a gravitational struggle. As it orbits, Jupiter's immense gravity pulls harder on one side than the other, stretching the moon like putty. Normally such tides would settle into a steady rhythm, but Io's orbit isn't perfectly circular. That's because its fellow moons Europa and Ganymede tug on it as well, pulling it slightly out of shape each time they pass. This resonance keeps Io's orbit elliptical, so instead of settling into peace, Io is constantly squeezed and released like dough in giant cosmic hands. That motion generates friction inside, enough to melt rock and turn its interior into a restless ocean of magma. The energy produced is staggering. Io releases about 100 times more heat than all of Earth's volcanoes combined. On Earth, volcanoes are dramatic but relatively rare. On Io, they are everywhere. At any given moment, dozens of them may be active, reshaping the landscape. Imagine standing on a plain of cooling sulfur, the air thin and toxic with the horizon dominated by enormous mountains. Then suddenly in the distance a plume rises like a colossal fountain. That is the everyday reality of Io. This surface is painted in strange colours because of this activity. Sulfur compounds create yellows, reds and oranges. Frozen sulfur dioxide forms plains of white. Here and there, lava flows add black scars across the landscape. If you could walk on Io, it would look nothing like the grey calmness of our own moon. Instead, it would resemble a surreal canvas, constantly repainted by eruptions, and above you, Jupiter would hang in the sky, massive, filling much of the horizon, reminding you of the force that drives all this activity. Despite its chaos, Io is a world of stability in another sense. It has likely been volcanically active for billions of years. This means it may be one of the oldest continuously active bodies in the solar system. Earth has cooled, Mars has quieted, but Io is still burning. That makes it a valuable window into processes we can't observe anywhere else. By studying Io, scientists learn about tidal heating, about how orbits interact, and even about how worlds outside our solar system might behave when locked close to giant planets. When Voyager passed by, it spotted Pele, one of the most dramatic volcanoes. Its plume rose 300 kilometers high and spread deposits of sulfur over a region the size of a continent. The name was fitting, after the Hawaiian goddess of volcanoes and fire. Since then, other spacecraft like Galileo in the 1990s and Juno more recently have continued to watch Io. Each time, they see new eruptions, new flows, new changes. Nothing stays the same for long. Io refuses to freeze in time. Even from Earth, astronomers can sometimes detect Io's eruptions. They appear as bright flashes of infrared light, heat signatures from fresh lava. That means that at any moment, if you pointed the right telescope, you might catch Io in the act of reshaping itself. It is never truly still. And yet, for all this drama, Io remains a small moon, just a little larger than our own moon, smaller than Earth, smaller than Ganymede or Callisto. Its power doesn't come from size, but from circumstance. It is the victim of a gravitational ballet that keeps it forever restless. In a way, that makes it a little tragic. Without Jupiter's pull and the nudges of its neighbours, Io might have been quiet, icy, forgotten. Instead, it has become unforgettable. As we drift deeper into Io's story, keep that image in mind. A small world circling a giant, forever pulled, forever reshaped. A world of constant eruption where silence is broken not by sound but by fountains of fire in the thin vacuum. It is strange, violent, and yet in its way soothing to watch from afar. Because in all its chaos, Io reminds us that even in the cold dark of space there are places where energy refuses to fade, where rest never comes, and where fire still has the last word. When we think of distant worlds now, we picture crisp photographs, coloured maps, and even fly-through animations. But there was a time when the only way to know another planet or moon was through a telescope no bigger than what you might see at a public observatory today. Imagine the winter of 1610 in northern Italy. A man named Galileo Galilei lifts a simple telescope to the sky. The air is cool, the night is clear, and Jupiter, bright and steady, hangs above the horizon. Galileo had improved the design of his instrument beyond what others had used before him. With it, he could see details that had always been blurred to the human eye. When he pointed it at Jupiter, he expected to see perhaps some cloud belts or a sharper disk. What he did not expect was to notice small points of light gathered near the planet, unlike background stars moving from one side to another night after night. At first, he may have doubted his. He made sketches marking the positions of these tiny lights relative to Jupiter. On one evening he saw 3, on another 4. Sometimes they lined up on one side, sometimes 2 on each. The positions changed, but their closeness to Jupiter never wavered. Stars would not do that. Stars were fixed in their constellations. These little lights were clearly bound to Jupiter, moving with it, orbiting it. Galileo realized he had found moons circling a planet other than Earth. The names we use now, Io, Europa, Ganymede, and Callisto, would come later. In that moment, they were simply companions to Jupiter, undeniable proof that not all things circled Earth. The importance of that discovery can be hard to feel now, when we're used to a universe filled with planets and moons. But in 1610, it was revolutionary. The dominant belief was that Earth sat at the centre of everything. The sun, the moon, the stars, all were thought to move around us. To say otherwise was not only a scientific challenge, but a philosophical and even religious one. Yet here was undeniable evidence. If little moons could orbit Jupiter, then perhaps Earth was not the centre after all. Galileo's telescope had quietly dismantled centuries of certainty. Io, though, was just a tiny dot in those first observations. Galileo had no way to know what made it special. To him, it was a point of light, no larger than a faint star. But that point of light, along with its companions, would shape the future of astronomy. Galileo wrote about what he saw in a book called Sidereus Nuncius, the Starry Messenger. He described the little bodies moving about Jupiter as if they were planets themselves. He even suggested that this system was a model for how Earth and other planets could orbit the Sun. The moons of Jupiter became evidence for the Copernican view of the solar system, a dangerous stance at the time, but one that would eventually reshape human understanding forever. When you picture Galileo at his telescope, think about the patience involved. The glass was not perfect, the magnification modest. The sky was never still, air shimmered and distorted the image. Yet night after night he persisted, marking dots on paper, slowly realizing the pattern. His notes reveal how careful he was, how unsure at first, and how gradually the truth revealed itself. In those sketches, Io appears as a wandering speck, moving back and forth across the planet's face. Nothing in those dots hinted at the furious volcanoes waiting to be discovered centuries later. For generations afterward, astronomers knew Io only as one of Jupiter's moons, one of 4 bright companions visible in even a small telescope. Through larger instruments, they could resolve Io into a tiny disk, but no surface detail was visible. It was simply a little orange-tinted ball circling Jupiter in less than 2 days. Compared to the grandeur of Saturn's rings or the storms of Jupiter itself, Io seemed plain. For a long time, it was overlooked, but those first glimpses remained important, not just for what they showed, but for what they proved. They demonstrated that Earth was not unique. They showed that other planets could hold on to their own systems, with satellites orbiting them just as the Moon orbits us. Io and its siblings became a quiet confirmation that the universe was richer, more complex, and less centered on humanity than people had once believed. Imagine living at that time when the sky was thought to be fixed and eternal. Then suddenly, a modest tube of glass and wood reveals movement, orbits, change. Io's discovery was not just a step in astronomy. It was a crack in the wall of an old world view. The Earth was not the centre. The heavens were not immutable. There were new worlds, and they were real, even if they looked like tiny sparks of light. Over the next centuries, astronomers refined their measurements. They tracked Io's orbit with precision. Its period, about 42 hours, was established. They noted its alignment with the other moons, how together they created patterns, sometimes eclipsing one another, sometimes vanishing into Jupiter's shadow. These events became so regular and predictable that by the 17th century, they were used to improve navigation. By observing when Io and the other moons disappeared into eclipse and reappeared, sailors could determine their longitude at sea. Io had become a kind of cosmic clock, helping guide ships across oceans. The idea that a small volcanic moon could aid in crossing Earth's seas is a reminder of how interconnected discoveries can be. A speck of light near Jupiter, first noticed in 1610, influenced not only philosophy, but also practical exploration. By the time telescopes improved enough to show Io's colour more clearly in the 19th and early 20th centuries, humanity already owed it a debt for making the world feel larger and more navigable. Still, its surface remained a mystery. Astronomers speculated. Some thought it might be icy, like Europa. Others imagined it cratered like Earth's moon. There was no way to know. Even with the best Earth-based observations, Io's true nature stayed hidden. Its reputation was quiet, unassuming, just another small world among many. That reputation would not last. If you think about it, that long period of mystery makes sense. Io is not visible to the naked eye, only through a telescope. It is overshadowed by Jupiter's brilliance, both literally and figuratively. For centuries, our moon and the planets received more attention because they showed detail. Io was background, important in theory but not in spectacle. All of that changed with the arrival of spacecraft. The first close look in the 1970s revealed the truth. Io was not quiet at all. But in the age of Galileo, none of that was known. To people then, the wonder was simply that it existed. It was a companion to Jupiter, moving in a dance that could be tracked, predicted, and relied upon. It was a new kind of body, proof that the sky was not limited to stars and planets alone. And for Galileo, who faced criticism and suspicion for his ideas, the discovery of Io and its siblings was a powerful piece of evidence. Even if he could not have guessed the violence on Io's surface, he could see the significance of its orbit. It told a story not just about one moon, but about the place of Earth in the cosmos. When you step outside on a clear night and point a modest telescope at Jupiter, you can still see what Galileo saw. The planet banded and bright, and beside it tiny specks of light that shift positions from night to night. One of those is Io. When you realise you're looking at the same site that shook the foundations of belief 4 centuries ago, it connects you to that moment in history. Even without detail, Io continues to play its role as a reminder that discovery often begins not with a full picture, but with a small, stubborn dot of light that refuses to fit old assumptions. In that sense, the The first glimpse of Io was less about volcanoes or sulfur plains and more about perspective. It was the spark that hinted at a bigger universe, one where Earth was just another planet, and moons could circle worlds far from us. From such a modest beginning, the story of Io grew into something extraordinary, and as time went on, each new tool, each new spacecraft, revealed more of the moon's restless nature. What began as a point of light became one of the most dramatic laboratories in the solar system, a place where gravity and fire play out their endless contest. And so, with Galileo's telescope, the story of Io entered human history. It was no longer just another unseen body drifting in the dark. It had become part of our knowledge, part of our map of the skies, and eventually a reminder that even the smallest dots of light can hold entire worlds within them, waiting for us to look closer. For a very long time, Io was a mystery tucked away near Jupiter, no more than a wandering speck to anyone who tried to catch it with a telescope. But the moment spacecraft came close enough to see it clearly, that speck transformed into something extraordinary. What they found was not the icy world that many had expected, nor a dull sphere pocked with craters like Earth's moon. What they found was a world that looked unlike anything else in the solar system. Every inch of its surface seemed alive with colour and change, painted in shades no one imagined a moon could carry. This was not the grey stillness of our moon, or the frozen shell of Europa, or the cratered surface of Callisto. This was something new. Io was not simply a moon. It was a world that broke every expectation. When Voyager 1 flew past in 1979, its cameras revealed the first true portraits of Io. Scientists back on Earth stared at the images in disbelief. The surface was splashed with yellows, reds, oranges, and blacks. It looked more like a landscape imagined in a dream than a natural satellite. At first glance, it resembled a pizza with melted cheese and scattered toppings, a description some scientists used half-jokingly, but that caught on quickly. But behind the humour was a shock. Moons were supposed to be quiet. Moons were supposed to be old and scarred with the slow record of impacts. Yet here was Io, smooth in places, freshly coated, constantly renewed. Where craters might have been, lava had already erased them. Instead of stillness, there was evidence of activity everywhere. The colours themselves told part of the story. Sulfur and sulfur dioxide are abundant on Io, and when they freeze or condense, they leave behind bright yellows and whites. Different forms of sulfur produce red and orange deposits. Volcanic ash adds black. The entire surface is a canvas of chemical reactions, repainted constantly by eruptions. What makes Io different is not just that it is volcanic, it is that it is the most volcanic body we know of. At any given moment, dozens of volcanoes are erupting across its surface. Some send lava fountains hundreds of kilometres high, others spread fresh flows that cover areas larger than cities. On Earth, volcanoes are dramatic but rare. On Io, they are simply part of the landscape, as ordinary as mountains or rivers are for us. To call Io unique is almost an understatement. Nowhere else in the solar system combines such constant activity with such strange chemistry. Europa may hide an ocean beneath its icy crust. Enceladus shoots plumes of water vapour into space. Titan has lakes of methane. Each moon has its wonders, but none erupt with the fury of Io. Its heat comes not from radioactive decay like Earth, but from the relentless squeezing and stretching of Jupiter's gravity. That tidal heating keeps the interior in turmoil. Imagine kneading dough, pressing and folding it again and again. The energy builds as friction and heat. On Io, that kneading never stops. The result is a world that never cools, never quiets, never rests. Standing on Io, if such a thing were possible, would be unlike standing anywhere else. The sky would be almost black, with Jupiter looming enormous above the horizon, banded with clouds and storms. The ground beneath your feet would be coated in sulfur frost, crunching faintly with each step. In the distance, a plume might rise silently into the vacuum, curling upward before arcing back down to paint the ground with fresh deposits. No air would carry sound, but the violence would be visible in every direction. The horizon would not be gentle hills but jagged mountains, some taller than Everest, shaped not by tectonic plates but by the stress of constant upheaval. Lakes of molten rock would shimmer with heat, glowing orange through cracks in the crust. In every direction, the surface would speak of change. What makes Io unlike any other is not only its activity but the way that activity connects to its parent planet. Io is locked in a dance with Jupiter that dictates its every move. The giant planet's magnetic field sweeps past Io, interacting with the particles escaping from its volcanoes. Electric currents flow between Io and Jupiter, creating auroras that shimmer around the poles of the giant planet. The relationship is not simply one of orbit. Io and Jupiter are bound in a system of exchange, the moon feeding material into space, the planet responding with magnetic forces and lights. No other moon is as tied to its planet in such a dramatic, visible way. When scientists first analysed Voyager's data, they realised just how extreme Io's environment was. The heat flow from its surface was enormous. The plumes stretched higher than anything ever seen before. One eruption, from a volcano named Loki, released more energy than all of Earth's volcanoes combined. Loki has remained one of Io's most active features, cycling through brightening and dimming phases as fresh lava erupts and then cools. To watch Io over time is to watch a world breathe fire again and again, never settling. In many ways, Io challenges our definition of what a moon should be. Moons are often thought of as passive companions, orbiting planets, but doing little on their own. Io is anything but passive. It reshapes itself constantly, interacts with its environment, and even influences Jupiter. When you consider the Galilean moons as a family, each with its own personality, Io is the unruly one. Ganymede is the giant, calm and large. Callisto is ancient, cratered and quiet. Europa is mysterious, hiding an ocean. Io is restless, unpredictable, never still. Together they form a system, but Io stands out as the one that refuses to conform. Part of what makes Io so unusual is the speed of its transformation. On Earth, landscapes change over centuries or millennia. Mountains rise, valleys erode, lava cools. On Io, landscapes can change within months. A lava lake may overflow and spread across a plain, covering it in fresh rock. A plume may deposit new material across hundreds of kilometers. Maps of Io quickly become outdated because the features they show are soon buried or altered. It is a world in fast motion, though seen from millions of kilometers away. Even its mountains are different. They are not the result of plate tectonics like Earth's ranges. Instead, they are massive blocks of crust uplifted by stresses from below. Many of them stand isolated, sheer cliffs rising from plains of sulfur frost. Some reach heights greater than 15 kilometers, rivaling or surpassing Everest. They rise abruptly, like solitary sentinels scattered across the surface. Their formation remains puzzling, but they remind us again that Io does not follow the same rules as other worlds. The more scientists study Io, the more it defies simple explanation. It is not merely a volcanic moon. It is a laboratory of tidal heating, chemistry, geology, and planetary interaction. Its uniqueness lies not in one feature but in the combination of them all. The constant eruptions, the strange colours, the giant mountains, the interaction with Jupiter's magnetic field, all of these weave together to create a world that has no twin. If you search the solar system for something similar, you would not find it. What makes this even more remarkable is that Io's uniqueness was hidden for so long. For centuries it was just a dot of light. No one suspected the violence waiting to be discovered. Even after telescopes revealed its orange tint, it gave little away. Only when spacecraft came close did it show its true face. That contrast between its quiet appearance from afar and its furious reality up close is part of what makes Io so fascinating. It reminds us that the universe is full of surprises, that assumptions often dissolve when we look more closely. In some ways, Io is a paradox. It is small yet powerful. It is a moon, yet it reshapes itself like a planet. It is trapped by Jupiter's gravity, yet it exerts influence in return. It is hostile to life as we know it, yet it teaches us about processes that may shape distant exoplanets. By existing as it does, Io expands our definition of what is possible. It shows that even small worlds can be dynamic, that moons need not be quiet, and that the solar system holds more variety than we once imagined. If you could float above Io, watching from orbit, you would see a surface that never seems to stay the same. Over here, a dark patch spreads as fresh lava emerges. Over there, a bright plume rises and falls. The colours shift as sulfur changes form, turning yellow here, red there, white in patches of frost. You could watch for weeks and never see the same world twice. It is this living quality, this constant change, that sets Io apart. And yet, for all its violence, Io has a kind of rhythm. The eruptions follow cycles, some more predictable than others. Loki brightens every few years as its lava lake overturns. Other volcanoes erupt sporadically, but often enough to be expected. The tug of Jupiter is relentless, ensuring that the energy never runs out. In its way, Io has settled into a pattern of chaos, a steady unpredictability. That paradox too is part of its uniqueness. When we call Io a world unlike any other, we mean not just in the solar system, but perhaps beyond. Astronomers have begun discovering exoplanets that orbit close to giant worlds, where tidal forces may heat them in similar ways. Io becomes a model for those distant systems, a case study in what happens when gravity and orbits conspire to create endless energy. It shows us that volcanic activity is not limited to Earth, that moons can burn just as brightly as planets. To gaze at Io through a telescope is still to see a small dot near Jupiter, but to know what lies beneath that dot is to see a world of extremes, a world that refuses to be ordinary. It is a reminder that appearances deceive, that even the smallest lights in the sky may hide landscapes stranger than anything imagined. Io's uniqueness lies not in one spectacular feature, but in the way all of them combine. It is the fiery heart of the outer solar system, a moon that behaves more like a restless planet, a world that breaks the mold in every possible way. When we think of the surface of a moon, we usually imagine stillness. Earth's moon is a quiet place. Its grey plains are covered in dust that has rested for millions of years, undisturbed except by the occasional meteor impact. Craters remained fixed in place, silent records of ancient collisions. Europa's crust is icy and cracked, but the cracks are frozen, unchanging to the naked eye. Callisto is ancient, its face a map of billions of years of impacts that never fade. But Io refuses to conform to this picture of stillness. Its surface is in motion, not through drifting tectonic plates like Earth, but through constant eruptions that rework the landscape. The restless surface beneath the silence is what makes Io unique. If you were to stand on Io, there would be silence in your ears, because the thin atmosphere cannot carry sound. But with your eyes, you would see motion and change all around. The ground beneath your feet might be a field of sulfur frost, pale yellow or white, crystalline and brittle. Across the horizon, dark flows might mark where lava has poured only weeks or months before. Plumes of sulfur dioxide might rise into the black sky, invisible except for the faint glow of sunlight reflecting off them, curling upward and falling back in great arcs. Lakes of molten rock might glow faintly through cracks in the crust, restless heat pressing upward. This world is never still. One of the first things Voyager revealed when it passed Io was that it lacked craters. On almost every other moon in the solar system, craters are the dominant feature. Impacts carve them into the surface, and because erosion is minimal, they remain for billions of years. The absence of craters on Io was astonishing. It meant that the surface was young, constantly renewed, resurfaced by volcanic activity. Wherever a crater might form, lava soon buried it. The surface is renewed so quickly that nothing ancient remains visible. It is like watching a chalkboard being wiped clean again and again, never allowing the past to stay etched on its face. The surface is restless because the forces within Io never cease. Jupiter pulls constantly, stretching and squeezing Io in its orbit. That motion generates heat, and the heat pushes upward. Unlike Earth, where volcanic activity is limited to certain regions, on Io it can occur anywhere. At any given moment there may be dozens of active eruptions, fountains of lava reaching into space. The flows cover vast areas, spreading new deposits across the plains. The mountains crumble under the stress. The crust cracks, shifts and reforms. This constant renewal makes Io's surface one of the youngest in the solar system. While our moon holds billions of years of history in its craters, Io rarely preserves anything older than a few million years, and often far less. The silence of Io is deceptive. From a distance, one might think of it as barren, lifeless, quiet. But beneath that silence is a storm of activity. If Io had an atmosphere thick enough to carry sound, it might be deafening. Eruptions would roar, lava would crackle, gases would hiss. But in the vacuum, all that fury plays out wordlessly. The contrast is striking. Absolute silence paired with relentless motion. It is a reminder that sound is not the only measure of activity, that worlds can be loud in action even when they are mute to our ears. The plumes that rise from Io's volcanoes are among its most remarkable features. Some reach more than 300 kilometers high, towering far above the surface. They spread outward like great umbrellas, depositing frost and ash across wide areas. These plumes are not like the explosive ash clouds we know from Earth's volcanoes. They are driven by the rapid release of gas, mostly sulfur dioxide, expanding into the vacuum of space. As the gas escapes, it freezes and falls back as frost, coating the landscape in bright white patches. From orbit, these deposits appear as giant circles marking the reach of eruptions. To see one of these plumes from the surface would be to witness an enormous, silent fountain stretching into space, arching gracefully back down. Beneath the plumes, lava lakes churn. Some of Io's volcanic features are so large they could swallow entire regions on Earth. Loki Patera, one of the most active, is a lava lake more than 200 kilometers across. Its surface darkens as it cools, then brightens again when fresh lava wells up from below. Over time, its surface overturns in great waves, replacing old crust with new. Observed from orbit, Loki brightens and dims in cycles, a sign of its constant renewal. Watching it is like watching a heartbeat, a steady rhythm of volcanic activity that never ceases. Other regions are dominated by vast flows that spread for hundreds of kilometers. These flows cool into dark plains, only to be covered again by the next eruption. In some places, the flows are so fresh that their heat can be detected even from Earth, glowing faintly in infrared. This means that Io's restlessness is not just a matter of distant history. It is ongoing, happening now as we speak. If you looked at Io through the right instruments tonight, you might catch one of these glowing patches, evidence of a surface in motion. The mountains of Io tell another part of the story. Unlike Earth, where mountains form from the collision of tectonic plates, Io's mountains rise through internal stresses. Blocks of crust are pushed upward, tilted, and broken. Some stand isolated, enormous ridges rising from plains of frost and lava. Many are taller than Everest, their sheer cliffs plunging downward for kilometers. These mountains are unstable, fractured by the same forces that raise them. Landslides cascade down their slopes, adding to the chaos of the surface. From orbit, they appear as jagged scars, reminders that Io's crust is under constant strain. What is striking about Io's surface is how quickly it erases its own past. Craters vanish beneath lava, mountains crumble, plains are buried. The surface never holds still long enough to preserve a long history. If you tried to map it, your work would quickly be outdated. Features shift, brighten, darken, appear, and vanish. It is a surface in flux, a place where permanence is impossible. This restlessness makes Io unlike any other moon. It is the only world we know that is so completely dominated by volcanic activity, so thoroughly reshaped by internal energy. For scientists, Io is both a challenge and a gift. Its restlessness makes it difficult to study in detail. Maps cannot stay accurate, predictions are hard, but it also offers a chance to see geological processes in action. On Earth, volcanoes are rare events. On Io, they are continuous. It is like having an entire planet-sized laboratory, where eruptions never stop, where you can watch the surface being renewed again and again. By studying Io, scientists learn not only about volcanic activity, but about the effects of tidal heating, the way gravity can reshape a world from within. The silence of Io's surface is also a reminder of how different it is from Earth. We are used to sound accompanying motion. On Io, all that motion occurs in a vacuum, in complete stillness. The ground may be reshaped every day, but no one would hear it. That silence gives Io an eerie quality. It is a world of constant change, but it changes in absolute quiet. If you stood there, you would see the horizon shift and the ground glow, but your ears would register nothing. It is a kind of silence that is difficult to imagine. Silence not of stillness, but of fury muted by thin air. The colours of Io's surface add to its strangeness. Sulfur takes many forms, each with its own colour. Bright yellow deposits mark areas of fresh sulfur frost. Reds and oranges mark places where it has been heated or chemically altered. Black patches mark fresh lava, still warm from eruptions. White patches mark sulfur dioxide frost, frozen from plumes. Together these colours create a landscape that is almost surreal. From afar it looks painted, as if an artist had splashed vivid pigments across the globe. Up close it would be even stranger, a patchwork of materials laid down and erased again and again. Io's surface is restless not only because of volcanic activity, but because of the constant interaction with Jupiter's magnetic field. The particles escaping from Io's volcanoes are swept into space, creating a torus of plasma around Jupiter. These particles rain back down onto Io, altering its surface chemistry. The moon is not just reshaped from within, but from without, caught in a dynamic exchange with its planet. This interaction adds another layer to the surface's restlessness, another reason why nothing stays the same. If you compare Io to Earth, the differences are striking. Earth's volcanoes are fueled by plate tectonics and mantle plumes. Io's are fueled by tides. Earth's surface holds ancient mountains and craters that last for hundreds of millions of years. Io erases its past quickly. Earth has oceans and air that carry sound and weather. Io has only silence and frost. Yet in both cases the surface is a reflection of the forces within. On Earth, life and water add complexity. On Io it is gravity and heat. Both tell stories of planets shaped by energy, but Io's story is one of extremes. What is most remarkable is that all this restlessness occurs on a moon no larger than our own. Io is not a giant planet or even the largest moon of Jupiter. It is relatively small, yet it outshines them all in activity. That contrast between its modest size and its furious surface is part of its fascination. It proves that even small worlds can be powerful, that size alone does not determine activity. The restless surface beneath the silence makes Io a world of paradoxes. It is loud in action, silent in sound. It is young in surface, old in orbit. It is small in size, immense in energy. It is violent, yet strangely beautiful. To gaze at it is to see a world caught in perpetual upheaval, never at rest. And as we carry this image forward, it becomes clear that Io's surface is not just restless for its own sake. It is restless because of the forces pulling at it, forces that come from beyond itself. When we speak of volcanoes on Earth, the imagination immediately leaps to mountains like Mount Etna, Mauna Loa, or Mount St. Helens. We think of molten rock pouring from vents, glowing rivers of lava creeping across the land, or explosive plumes that reach high into the sky. These are some of the most powerful natural forces our planet can produce. They reshape landscapes, destroy what lies in their path, and create new land from molten depths. Yet when we compare Earth's volcanoes to those on Io, they seem almost modest. The volcanoes of Io are not only more numerous but more energetic, more persistent and more spectacular than anything Earth can offer. When Voyager first revealed Io's volcanic activity, it was not subtle. Cameras captured enormous plumes erupting above the surface, reaching hundreds of kilometers into space. At first, scientists were not certain what they were seeing. No one had expected an active world, and the sight of fountains rising far above the horizon seemed almost unbelievable. But as more data came in, the reality became undeniable. Io was covered with volcanoes, and they were erupting right at that very moment. For the first time in history, humanity had witnessed active volcanism on another world, and it outshone our own. One of the most striking differences between Earth's volcanoes and Io's is scale. On Earth, an eruption plume might rise 10, maybe 20 kilometers. The largest eruptions in history, like Krakatoa in 1883, sent ash more than 40 kilometers into the atmosphere, high enough to spread around the globe. On Io, however, plumes commonly rise more than 100 kilometers, and some exceed 300. Imagine standing on the surface, looking up into the black sky, and seeing a column of gas and particles arcing far above you, disappearing into the distance before curving back down. These plumes are so large that they are visible from orbit, casting vast circular shadows across the surface. Compared to this, Earth's eruptions seem restrained, confined to the lower reaches of the sky. The energy that fuels Io's volcanoes is also greater. On Earth, volcanism is driven by heat from within, a combination of radioactive decay and residual heat from formation, along with the movement of tectonic plates. On Io, the heat comes from tidal forces, the endless squeezing and stretching caused by Jupiter's gravity and the influence of neighbouring moons. This energy is immense, enough to melt large portions of Io's interior. The result is a continuous supply of molten rock pressing upward, looking for release. Where Earth's volcanoes can fall silent for centuries between eruptions, many of Io's are in constant motion, erupting again and again without pause. Among the most famous is Loki Patera, a massive volcanic depression that contains the largest active lava lake in the solar system. It stretches more than 200 kilometers across, an area large enough to cover entire regions of Earth. The surface of the lava lake continually overturns, cooling in dark crust before sinking and being replaced by fresh molten rock. From orbit, Loki brightens and dims in cycles, a heartbeat of volcanic activity that never truly stops. The energy it releases surpasses that of any single volcano on Earth. Some scientists estimate that at peak activity, Loki produces more heat than all of Earth's volcanoes combined. Another extraordinary feature is Pele, named after the Hawaiian goddess of fire. When Voyager first observed it, a plume extended more than 300 kilometers into space, and the deposits it left behind formed a giant red ring more than 1,000 kilometers across. This plume was not a one-time event. Pele remains one of Io's most active volcanoes, regularly spewing material that coats the surrounding landscape in vivid reds and oranges. These colours come from sulfur compounds, heated and altered by the violence of the eruption. The result is a surface painted in brilliant hues, visible even from great distances. On Earth, lava flows are measured in kilometers or tens of kilometers. On Io, flows can extend for hundreds of kilometers. One eruption in the 1990s produced a flow more than 400 kilometers long, spreading across plains and burying everything in its path. These flows move quickly, sometimes advancing at speeds of several kilometers per day. In comparison, Earth's lava flows are often measured in meters per hour, creeping slowly forward. The sheer scale of Io's flows highlights the difference in energy. This is not a world of slow oozing. It is a world of sweeping, relentless floods of molten rock. The composition of Io's lavas also adds to its uniqueness. On Earth, most lava is basaltic, dark and fluid, or andesitic, thicker and more explosive. On Io, some lavas are so hot they must be ultramafic, similar to the ancient lavas that shaped Earth billions of years ago. These lavas may reach temperatures of 1,600 degrees Celsius or more, hotter than any eruption seen on Earth in the present day. This suggests that Io is not just active, but active in a way that mirrors the earliest days of Earth's volcanic history. In a sense, to watch Io erupt is to glimpse the kind of processes that shaped our own planet long ago. The sheer number of volcanoes on Io is staggering. More than 400 active volcanoes have been identified, and many more dormant or temporary features likely exist. At any given time, dozens are erupting. From orbit, infrared images show glowing hotspots scattered across the surface, each one a sign of molten rock breaking through. This is not a rare event. It is a continuous condition. Io's surface is essentially a volcanic plain, a world where eruptions are as common as rainfall is on Earth. One of the fascinating consequences of this activity is the way it interacts with space. Io's plumes and flows do not remain confined to the surface. Much of the material escapes into space, forming a vast torus of plasma that encircles Jupiter. This torus glows in ultraviolet light, visible to spacecraft instruments, and interacts with Jupiter's magnetic field. The result is auroras on Jupiter, shimmering displays of light powered in part by Io's volcanic outbursts. No Earth volcano could ever influence our planet in this way. On Io, the link between volcanism and space environment is direct and constant. The violence of Io's volcanoes raises questions about the experience of being near them. On Earth, an eruption is a sensory overload. You hear the roar, feel the ground tremble, see the clouds of ash. On Io, there would be no sound, no air to carry it. You would see fountains of molten rock and plumes of frozen gas, but you would hear nothing. The ground might shift beneath you, but it would do so in eerie silence. The only signs of violence would be visual: the glow of lava, the arc of a plume, the shifting of the horizon. That contrast between sight and silence adds to the alien nature of Io's eruptions. From a scientific perspective, Io's volcanoes are invaluable. They show us how tidal heating can drive geology, how gravitational interactions can fuel activity far greater than what size alone would suggest. They remind us that volcanism is not confined to Earth, that it can thrive on small moons as well as giant planets. They also help us understand the past. The ultramafic lavas of Io echo the lavas that once covered early Earth, offering a window into a time we cannot observe directly. Studying Io gives us a chance to look back in time as well as across space. The persistence of Io's volcanoes is another striking feature. On Earth, volcanoes often go dormant for centuries, awakening only occasionally. On Io, some features have been erupting for decades, possibly centuries. The energy supply is constant, the gravitational kneading never-ending. This persistence means that Io is unlikely to quiet anytime soon. As long as it orbits Jupiter, as long as the gravitational dance continues, its volcanoes will outshine those of Earth. Even the way Io's volcanoes distribute heat is unusual. On Earth, volcanic heat is localized, concentrated in specific regions. On Io, heat is spread across the globe. Plumes and flows appear everywhere, from equator to poles. This global distribution is evidence of the internal energy at work, heating the entire moon, not just isolated regions. The result is a world where no place is safe from eruption, no region immune to change. The surfaces shaped by these volcanoes are varied. Some areas are covered in smooth plains of frozen sulfur dioxide deposited by plumes. Others are darkened by lava flows, rough and fractured. Still others are dominated by mountains pushed up by the stress of constant upheaval. Together they create a patchwork of landscapes, each one temporary, each one destined to be buried or altered by the next eruption. Maps of Io are always provisional, snapshots of a surface that refuses to hold still. The volcanoes also create beauty. Though they are violent, the colours they produce are striking. Rings of red and orange mark plume deposits. Bright yellows and whites mark fresh frost. Dark scars mark new lava. These contrasts create a landscape that is chaotic but vivid, violent but beautiful. From afar, it looks like a painting constantly in progress, each eruption adding new strokes, each plume altering the palette. For astronauts, if they ever visit, Io would be the most hazardous of destinations. The surface is unstable, the eruptions unpredictable, the radiation from Jupiter intense. Yet it would also be one of the most spectacular. To witness a plume rising hundreds of kilometers into space, to see a lava lake overturn before your eyes, to watch a surface change in real time, these would be experiences beyond anything Earth could offer. Io is dangerous, but it is also mesmerizing, a stage where volcanism plays at its grandest scale. When we say Io's volcanoes outshine Earth's, it is not just metaphor. They truly do produce more energy, reach greater heights, cover greater distances, and persist longer. They redefine what volcanism can be, expanding our sense of possibility. They remind us that Earth, though active, is not the only volcanic world, and not the most dramatic one. In the grand theatre of the solar system, Io holds the spotlight, erupting continuously, reshaping itself in silence and sending its influence far beyond its surface. And as we watch those volcanoes from afar, glowing as hot spots in infrared images, arching as plumes in spacecraft photographs, spreading as flows across the plains, we see a world that cannot rest. Io's volcanoes are its heartbeat, its breath, its identity. They are the reason it is unlike any other, the reason it captivates us, the reason it continues to teach us. When we look at Io and see its eruptions, its plumes, and its ever-changing surface, it is easy to think of it as a world that simply chose to be volcanic, as though it were inherently restless from the beginning. But the truth is that Io's fury is not born entirely from within. The energy that powers its eruptions, that melts its rock, that keeps its surface in constant motion, comes from outside. It comes from the gravity of Jupiter, and from the delicate but relentless dance of orbits that Io shares with its neighbours. Without that pull, Io would be a frozen moon, quiet and unremarkable. With it, it becomes the most violent body in the solar system. Jupiter is an enormous planet, the largest in our solar system, more than 11 times wider than Earth. Its gravity is so powerful that it shapes not only the orbits of its moons, but also influences comets, asteroids, and even the structure of the solar system itself. For Io, orbiting at a distance of about 422,000 kilometers, Jupiter's pull is overwhelming. The difference in gravity from the side facing Jupiter to the side facing away is enough to stretch the moon, elongating it slightly, pulling it back and forth as it moves around the planet. This tidal force is the key to Io's activity. If Io's orbit were a perfect circle, the stretching would be constant, and the moon might eventually settle into a stable shape, warmed but not overwhelmed. But Io's orbit is not circular. It is slightly elliptical, stretched out so that at times Io is closer to Jupiter, and at other times farther away. As it moves along this orbit, the strength of Jupiter's pull changes. When Io is closer, the pull is stronger. When it is farther, the pull is weaker. This constant shifting means that Io is forever squeezed and released, like a ball of clay pressed rhythmically in an unseen hand. The friction generated by this endless flexing produces enormous heat inside the moon, enough to melt rock into magma. But why does Io's orbit remain elliptical? Normally, tidal forces tend to circularize orbits, smoothing them out over time. The answer lies in Io's relationship with its sibling moons, Europa and Ganymede. These three moons are locked in what is called an orbital resonance. For every time Ganymede orbits Jupiter once, Europa orbits twice, and Io orbits 4 times. This resonance keeps their gravitational interactions in balance, but it also ensures that Io's orbit never settles into a circle. Each time Io and Europa line up, their gravity tugs on one another, nudging Io's orbit slightly, maintaining its eccentricity. As a result, Io never escapes the cycle of stretching and releasing. The resonance traps it in a perpetual state of tidal heating. The effect of this is staggering. On Earth, the tides raised by the moon shift the oceans back and forth, but the land itself only moves by centimetres. On Io, the solid surface is lifted and lowered by as much as 100 metres as it orbits Jupiter. Imagine standing on solid ground and feeling it rise and fall, the height of a skyscraper every time the moon completes its orbit, which takes less than 2 days. This constant flexing is the true source of Io's fury. Inside Io, the rock cannot withstand this stress without changing. Friction builds, heat accumulates, and the interior becomes partially molten. Pockets of magma form, some merging into vast reservoirs. Pressure builds until it finds release at the surface, bursting forth in eruptions that dwarf anything on Earth. The connection is direct. Without Jupiter's gravity, there would be no volcanoes. Io is a product of that pull, a world reshaped from the inside out by forces far beyond its own size. The process is known as tidal heating, and Io is its most extreme example. Other moons in the solar system experience it too, though in different ways. Europa's ice shell is cracked and shifted by tidal heating, and beneath it lies a global ocean kept liquid by the same process. Enceladus, around Saturn, experiences tidal heating that powers geysers spraying water vapour into space. But Io is closer to Jupiter, and the effect is far more violent. Instead of melting ice, it melts rock. Instead of cracks and geysers, it produces lava and plumes of sulfur. Io is the poster child of tidal heating taken to its limit. This heating explains why Io's volcanoes outshine Earth's. On Earth, volcanism is localized and driven by plate tectonics. On Io, it is global, driven by an entire moon flexing under the pull of a giant planet. The difference in scale of energy input is enormous. The heat Io releases is about 100 times greater than that of all Earth's volcanoes combined. This is not a coincidence. It is the natural consequence of being caught in Jupiter's gravitational grip. If you picture Io's orbit from above, you see a small world circling a giant, forever locked in the same face-to-face orientation because of tidal locking. Io always shows the same side to Jupiter, just as our moon does to Earth. But unlike our moon, Io's orbit is not calm. Its path is slightly stretched, so each lap around Jupiter brings new stresses, new deformations, new heating. The moon is both a captive and a participant in this dance, trapped, but also energized. It cannot escape without breaking the resonance, and the resonance holds firm because of the intricate balance between Io, Europa and Ganymede. The resonance is a kind of cosmic chain. Io pulls on Europa, Europa pulls on Ganymede, and together they lock into ratios that repeat endlessly. This resonance prevents the system from degrading, ensuring that the gravitational tug-of-war continues indefinitely. For Io, that means no peace, no stability. It will never settle, never cool, never quiet. Its fate is sealed by the geometry of orbits, the mathematics of resonance, the unyielding pull of gravity. Jupiter's role in this is immense. Its mass, more than 2.5 times that of all the other planets combined, dominates the system. Its gravity is not a gentle tug, but an overwhelming force, shaping the lives of its moons in ways we are only beginning to fully understand. For Io, that gravity is destiny. It ensures that the surface will never resemble our moon's quiet plains. It ensures that eruptions will continue as long as the orbit remains as it is. Io's fury is not an accident, but an inevitability, written into the very structure of its orbit. From Earth, we cannot feel this pull directly. We see only the results, the eruptions, the plumes, the glowing lava flows. But to imagine Io's perspective is to imagine a world that is never still, whose very body rises and falls with each orbit, whose interior is constantly kneaded like dough. It is to imagine a world whose fury is not chosen but imposed, a fury that comes from being caught between giants, pulled and pushed without relief. Scientists use Io as a model to understand tidal heating elsewhere. Exoplanets orbiting close to giant worlds may experience similar forces. Some of them may be volcanic, like Io, erupting continuously as they are squeezed by gravity. Others may be heated enough to sustain oceans beneath ice, like Europa or Enceladus. Io shows us the extremes, the upper bound of what tidal heating can do. It proves that gravity is not just a force that holds orbits, but also a source of energy that can transform worlds. The relationship between Io and Jupiter is not one of balance, but of dominance. Jupiter dictates Io's activity, its surface, its fate. Yet in return, Io influences Jupiter as well. The material ejected from Io's volcanoes escapes into space, forming the Io plasma torus, a giant ring of charged particles around Jupiter. This plasma interacts with Jupiter's magnetic field, producing auroras at the planet's poles. In this way, Io's fury feeds back into the giant planet, creating lights that shine even from Earth. The gravitational pull flows one way, but the volcanic response radiates back, connecting moon and planet in a cycle of influence. To say that Jupiter's gravity shapes Io's fury is to say that without Jupiter, Io would be something else entirely. It would likely be a frozen moon, covered in ice and rock, scarred by craters, quiet and still. It would resemble Europa, or Callisto, or any number of other outer moons, but Jupiter refuses to let it rest. By pulling on it, by keeping it in resonance, by squeezing and releasing it endlessly, Jupiter has transformed Io into a world of extremes. Its fury is the shadow of Jupiter's might, the surface expression of forces that operate on a scale far beyond human experience. And so, each time Io erupts, each time lava spreads across its plains, each time a plume rises into space, it is Jupiter's gravity that we are seeing. The volcanoes are not merely Ios. They are the fingerprints of Jupiter's pull, the visible outcome of an invisible hand. Io's violence is Jupiter's gift and Jupiter's curse. And as we watch from afar, we see not just a moon in turmoil, but the power of gravity itself, shaping a world in fire and silence. When we look at Io from the outside, we see eruptions and plumes, rivers of lava and vast plains coated with sulfur. But beneath that restless surface lies a deeper rhythm, a constant back and forth that is not random at all. It is the rhythm of tides, not tides of water as we know on Earth, but tides of rock, pulled and released by Jupiter's immense gravity and the precise patterns of orbital resonance with Europa and Ganymede. This rhythm is the true conductor of Io's fire, the silent dance that never ends, a dance of tides and fire that has lasted for billions of years. On Earth, we know tides from the ocean. Twice a day water rises and falls, drawn by the pull of the moon and the sun. But Earth's land barely moves, shifting by only centimetres. On Io, there are no oceans to rise and fall, but the entire crust itself is pulled upward and downward by as much as 100 meters during each orbit. Imagine standing on solid ground that slowly lifts you higher than the tallest skyscraper and then lowers you again, all in less than 2 days. That is Io's experience. This constant flexing is the heartbeat of the moon, the hidden motion that drives its visible eruptions. The reason for this relentless movement lies in the gravitational relationships among Jupiter's 3 closest large moons. Io orbits Jupiter every 1.77 days. Europa takes about 3.55 days, exactly twice as long. Ganymede takes about 7.15 days, exactly 4 times as long as Io. This relationship is called a Laplace resonance, and it keeps their orbits locked together. Every time Io completes 4 orbits, Europa has completed 2, and Ganymede 1. Each time they line up, the slight gravitational nudges keep Io's orbit slightly elliptical. That small eccentricity is enough to ensure that Io is pulled harder when close to Jupiter and less hard when farther away, setting up the endless squeezing that produces heat. Without this resonance, Io's orbit would eventually settle into a circle and the heating would diminish. Instead, the resonance keeps it trapped in this cycle forever. Think of it like a dancer caught between partners. As Io moves, Jupiter pulls it one way, Europa tugs slightly another, and Ganymede balances the rhythm from farther out. Io cannot step away from this dance, cannot rest, cannot break the pattern. Its orbit is like a musical beat that never fades, a cycle that continues without pause. With every orbit, its body is flexed and twisted, and with every flex, heat builds in the interior, rising until the crust cannot contain it. Then the fire bursts forth at the surface, a direct expression of this gravitational choreography. The heat generated inside Io is immense. Estimates suggest that the moon produces more than 100 trillion watts of heat energy, far more than Earth despite its smaller size. On Earth, much of the heat escapes gradually through plate tectonics, hydrothermal vents, and occasional eruptions. On Io, there is no such balance. The heat builds and builds, and the only way to release it is through volcanism. That is why the surface is so dominated by eruptions. The dance of tides does not allow Io to cool. It continually stirs the interior, continually melts rock, continually forces it upward. The eruptions themselves follow the rhythm of this dance. Some volcanoes brighten and dim in cycles that may be linked to the orbital positions of the moons. When Io is pulled more strongly, the stresses may open cracks and release magma. When the stresses ease, eruptions may quiet for a time. The pattern is not random, but tied to the invisible movements of gravity. Scientists tracking Io's activity have noticed that certain eruptions recur on timescales that match the orbital resonances, suggesting that the dance itself sets the tempo. If you imagine Io's interior, it is not a solid sphere of rock, but a body riddled with molten regions, perhaps even with a global layer of partially molten rock beneath the crust. This layer acts like a reservoir, storing the energy of the tides until it bursts out. In this way, Io is like a drum, its skin stretched and released, its interior resonating with each beat. The eruptions are the notes of that drum, audible not in sound but in light and heat, visible from across the solar system. The dance of tides and fire does not happen in isolation. It influences and is influenced by the space environment around Jupiter. As Io erupts, it ejects material into space, adding particles to the plasma torus that encircles Jupiter. These particles interact with Jupiter's magnetic field, producing auroras at the poles of the giant planet. Thus, the dance extends beyond Io itself. The tides produce fire, the fire produces plasma, the plasma produces light in Jupiter's atmosphere. It is a chain of influence that begins with gravity and ends with auroras that shine brighter than anything on Earth. The beauty of this dance lies in its inevitability. Gravity is unyielding and resonance is stable. Unless something disturbs the system on a massive scale, Io will continue to orbit, continue to flex, continue to erupt. It has done so for billions of years and will likely continue for billions more. The volcanoes we see today are not temporary accidents, but the surface expressions of a process that is as permanent as the orbits themselves. The dance ensures that Io will never know the stillness that other moons enjoy. It will always be reshaped, always be renewed, always be restless. On Earth, our volcanoes connect us to the deep processes of the planet, reminding us that the surface is not separate from the interior. On Io, the connection is even more direct. The surface is the interior, bursting forth again and again, renewed by the pull of tides. The dance strips away the boundary between inside and outside. Everything is exposed, everything is changing. To watch Io is to watch geology in fast motion, sped up by forces far beyond what Earth experiences. The dance also reminds us of the interconnectedness of celestial bodies. Io's activity is not just about Io. It depends on Europa and Ganymede, on their alignment, on their steady tugging. Without them, the resonance would fail. Without Jupiter, there would be no pull at all. Io's fury is not its own alone. It is the product of a system, a network of gravitational relationships that keep it alive with fire. In this way, Io's volcanoes are the visible sign of a cosmic collaboration, the outcome of a dance with partners it cannot escape. For scientists, the dance of tides and fire is a natural laboratory. It shows how orbital mechanics translate into geology, how the invisible force of gravity can produce visible changes in rock and landscape. It helps us understand other moons and planets, and even distant exoplanets. Worlds that orbit close to giant planets may experience similar heating, producing volcanism or oceans beneath ice. By studying Io, we learn not only about a moon in our own solar system, but about the possibilities of worlds far away. Imagine drifting above Io in a spacecraft, watching its surface below. You might see glowing lava lakes darkening and brightening as they overturn. You might see plumes arching high into the black sky, their deposits spreading in wide circles. You might see mountains cracking and collapsing, new flows spreading across the plains. All of this would be the direct result of the dance, the fire released by tides. Each eruption would be a reminder of the unseen forces at work, the gravity pulling and releasing, the orbits resonating in harmony. The longer you watch, the more you realize that Io is not just erupting randomly. It is responding to a rhythm that is as steady as the movement of the moons themselves. The eruptions are part of a pattern, part of a dance that has been going on for as long as Io has existed in its orbit. It is not chaos, though it looks chaotic. It is order expressed in fire, structure expressed in eruptions. The dance of tides and fire is not an accident. It is a law written into the very fabric of Io's orbit. And so Io continues, forever pulled, forever reshaped, forever erupting. Its volcanoes are its voice, its way of expressing the gravity that acts upon it. Each plume, each flow, each lava lake is a verse in a song that has no end, a song composed by Jupiter, Europa and Ganymede, and performed endlessly by Io. To witness it is to see gravity made visible, tides transformed into fire, a dance that stretches from the interior of a moon to the auroras of a giant planet. When you look at Jupiter through a telescope, what you see is not only a massive planet, but also 4 bright specks that hover close to it. They are its largest moons, discovered by Galileo more than 4 centuries ago, and they are often called the Galilean moons in his honour. Io is the innermost, then comes Europa, followed by Ganymede, and farther still, Callisto. To the eye, they seem like simple companions circling their giant host, but their relationship is anything but simple. They're bound together by gravity in a delicate balance that has lasted since the solar system was young. That balance, that endless tug of Jupiter's moons, is what sustains Io's violence. The orbits of Io, Europa and Ganymede are linked in what astronomers call a Laplace resonance. This resonance is a repeating pattern, precise and stable. For every 4 times Io orbits Jupiter, Europa orbits twice, and Ganymede orbits once. The ratios line up exactly, so that the moons return to the same relative positions over and over. It is as though they are dancers moving in perfect synchrony, never colliding, never drifting apart, but repeating the same steps endlessly. This resonance ensures that their orbits remain stable, but it also ensures that Io's orbit stays slightly stretched, slightly eccentric, never a perfect circle. That small imperfection makes all the difference. Io, being the closest, feels Jupiter's gravity most strongly. Each time it moves closer in its orbit, it is pulled a little harder, stretched a little more. Each time it moves farther, the pull lessens. Normally, over millions of years, this stretching would fade. The orbit would smooth out, circularizing under the influence of tides. But because Europa and Ganymede tug on Io with every alignment, they keep it off balance. They maintain its eccentricity, ensuring that it never escapes the endless flexing that generates its heat. In this way, the outer moons are as responsible for Io's volcanoes as Jupiter itself. The tug is subtle but persistent. Imagine walking along a path, and with every few steps someone gives you a small nudge to one side. Alone, you might straighten your stride, but with repeated nudges, you will always be kept slightly off balance. That is what Europa and Ganymede do to Io. They prevent it from finding stability. They keep it locked in a cycle of stress and release, stress and release. The result is heat, pressure, and ultimately, fire bursting from its surface. Europa and Ganymede do not experience the same level of heating because they orbit farther away. The gravitational pull on them is weaker, and their eccentricities are smaller, but they too are shaped by the resonance. Europa's icy crust is cracked and fractured, evidence of stresses beneath. Beneath that ice lies an ocean of liquid water, kept warm by tidal heating. Ganymede, the largest moon in the solar system, shows signs of past activity, though it is quieter now. Together, these 3 moons form a chain of influence. Io burns, Europa flows with hidden oceans, and Ganymede bears the scars of a once more active past. Each one owes its state to the same gravitational choreography. Callisto, the 4th Galilean moon, lies farther out and is not part of the resonance. Its surface is ancient and heavily cratered, unchanged for billions of years. It is the quiet one, the spectator. In contrast, Io, Europa and Ganymede are the dancers, caught in step with Jupiter's gravity, their lives intertwined. Callisto shows us what Io might have been without the endless tug, a silent relic of the early solar system. Io, by comparison, is alive with violence, proof that even small tugs, repeated endlessly, can transform a world. The precision of the resonance is remarkable. If Io orbited just a little faster or slower, the alignment would break down. If Europa or Ganymede shifted, the pattern would unravel. Yet the system is stable, locked together by gravity in a way that can last for billions of years. This stability ensures that Io's activity is not a temporary condition, but a permanent one. As long as the resonance holds, the volcanoes will not fade. The endless tug of Jupiter's moons guarantees that Io will remain restless. From a human perspective, it is difficult to grasp the timescales involved. We think of volcanoes as brief events, eruptions that last days, weeks, or years. But Io's volcanism has lasted for eons, and will continue for eons more. The tugs of Europa and Ganymede do not weaken with time. They repeat with every orbit, every alignment, every cycle. The persistence of this dance means that Io's surface will always be renewed, its history always erased, its landscape always temporary. For scientists, this interconnectedness is a lesson in how celestial bodies influence one another. Planets and moons are not isolated. They are part of systems, networks of gravitational relationships that shape their geology and climate. Io teaches us that a small moon can be transformed completely by the tugs of its neighbours. It also suggests that similar processes may occur in other planetary systems. Exoplanets orbiting close to giant worlds may experience tidal heating from similar resonances, producing volcanism, oceans, or other forms of activity. The endless tug we see at Jupiter may be repeated countless times across the galaxy. If you imagine Io from above, circling Jupiter, you see more than just a moon and a planet. You see a system of orbits, each linked to the others. Io moves quickly, Europa more slowly, Ganymede slower still. Their alignments shift and repeat, creating a rhythm that never breaks. That rhythm is invisible to the eye, but its effects are written on the surfaces of the moons. Io's eruptions, Europa's ice, Ganymede's ridges, all are the visible results of the endless tug. It is as though gravity writes its music into the geology of worlds, each note a volcano or a crack or a mountain. The beauty of this system is that it is both delicate and robust. Delicate because the resonance depends on precise ratios that might seem easy to disrupt. Robust because gravity is unyielding, and once established, the resonance is self-reinforcing. Each tug keeps the pattern alive, each orbit sustains the balance. For Io, this means that escape is impossible. It cannot drift into calmness. It cannot choose stillness. It is locked in place, caught between Jupiter's gravity and the nudges of its siblings, forever restless. Europa and Ganymede, though less violent, also owe their natures to this tug. Europa's ocean would freeze solid without the heat from tidal flexing. Ganymede might be just another quiet moon without the resonance. Instead, all three are marked by their shared relationship. The endless tug has made Io a world of fire, Europa a world of hidden water, and Ganymede a giant with a complex history. They are three faces of the same phenomenon, three outcomes of the same gravitational pattern. To appreciate Io's fury fully, we must see it not as an isolated moon but as part of this system. Its volcanoes are not only the result of Jupiter's pull, but of the combined influence of its siblings. Each eruption is a testament not just to the might of Jupiter, but to the subtle persistence of Europa and Ganymede. Without them, the resonance would collapse, the orbit would circularize, and Io would cool. Its surface would harden, its volcanoes would fade, its restlessness would cease. In that sense, Io's fire is a gift from its siblings as much as from its giant parent. The endless tug of Jupiter's moons is a reminder that balance in space is rarely simple. It is not just one body influencing another, but many bodies locked together shaping each other's destinies. Io's fury is Europa's doing as much as Jupiter's. Ganymede's presence keeps the chain intact. Callisto, distant and detached, shows what absence from the resonance means. Together they form a family, and like many families, their interactions are complex, their influence on one another inescapable. As we drift onward in Io's story, we carry with us the knowledge that its violence is not solitary. It is the outcome of an endless tug, a dance with its siblings, a resonance that sustains its fire. And while the volcanoes and plumes are what we see, what lies beneath is this invisible connection, this gravitational bond that shapes the fate of moons and planets alike. When spacecraft first brought us close to Io, one of the most striking impressions was its colour. Unlike the grey and dusty surface of our own moon, unlike the icy whites and blues of Europa, or the dark ancient crust of Callisto, Io glowed with a palette that seemed almost unnatural. Yellows, reds, oranges and whites sprawled across its surface, interrupted by patches of black and green. It looked more like a painter's canvas than a natural world. Scientists soon understood that these colours were the mark of sulfur, in its many forms and states, painted and repainted by constant eruptions. Io is a world where the surface is not only reshaped, but recoloured again and again, a landscape painted in sulfur. Sulfur is an element familiar to Earth. We smell it in volcanic gases, in the sharp scent of rotten eggs carried by hydrogen sulfide. It burns with a blue flame, leaving behind a pale residue. But on Io, sulfur is everywhere, spread across the plains, filling the airless sky with particles, settling back onto the ground as frost and crystals. Its abundance is the reason Io's surface shines in those vivid hues. The constant volcanic eruptions release sulfur and sulfur dioxide in vast quantities, and as these compounds freeze and condense, they coat the surface in layers of colour. The result is a landscape unlike any other in the solar system. The colours are not random but the product of chemistry. Bright yellow marks regions where sulfur is freshly deposited in crystalline form. Deeper reds and oranges appear where sulfur has been heated, transformed into other allotropes. White patches mark sulfur dioxide frost, frozen out of the thin atmosphere or condensed from plumes. Black streaks and plains mark fresh lava flows, where molten rock has buried older deposits. Greens sometimes appear where sulfur compounds mix or where unusual chemical reactions take place. Together, these colours create a patchwork that changes from month to month, year to year, as eruptions repaint the surface. If you could stand on Io, the ground beneath you might appear pale yellow, crunching softly underfoot like frost. In the distance, a dark plain of basaltic lava might stretch across the horizon, its surface still faintly glowing from recent eruption. Around the edges of a plume deposit you might see a ring of red, fading into orange, then yellow, then white. The variety would be overwhelming, a kaleidoscope of colours produced not by vegetation or weather, but by the chemistry of sulfur under extreme conditions. The silence of the vacuum would make it all the more surreal. The ground would shimmer with colour, but the world itself would remain utterly still, except for the sight of distant plumes arching high into the black sky. From orbit, the effect is even more dramatic. The entire moon appears like a mottled sphere, bright in places, dark in others, with patterns that shift as eruptions repaint the surface. Scientists comparing images over time see clear evidence of change. A region once bright may darken, coated in fresh lava. Another once dark may brighten, covered in frost. Plume deposits spread like giant circles, hundreds of kilometres across, easy to identify even from afar. Io is like a canvas that never dries, a painting that is always in progress. The source of all this sulfur is Io's interior. Volcanic eruptions spew out sulfur gases, which condense into solids when they reach the surface or escape into space and return as frost. On Earth, sulfur is a minor component of volcanic activity, mixed with water vapour, carbon dioxide and other gases. On Io, water is almost absent, and sulfur dominates. That difference explains much of Io's strangeness. Instead of rivers and oceans of water, it has lakes of molten sulfur. Instead of clouds of steam, it has plumes of sulfur dioxide. Instead of landscapes carved by erosion, it has landscapes painted by chemical frost and lava. The presence of sulfur in so many forms also gives Io's surface a dynamic quality. Sulfur changes state easily, shifting from solid to liquid to gas at relatively low temperatures compared to rock. As a result, the surface deposits are fragile, easily sublimated or melted by new eruptions. A bright white frost field may vanish as sunlight warms it, or as a nearby eruption buries it. A red ring may fade into yellow as the sulfur cools. These constant transformations make the surface seem alive, even though it is uninhabitable by life as we know it. One of the most spectacular sights on Io are the giant rings left by plume deposits. When a plume erupts, it spreads sulfur dioxide and sulfur particles high into space. As the plume falls back, it creates a circular pattern on the surface, often hundreds of kilometres wide. These rings appear as bright patches in spacecraft images, sometimes overlapping, sometimes fading into one another. They are evidence of the sheer scale of Io's volcanic activity, and they add to the painted appearance of the surface. Some plumes, like Pele, leave behind especially vivid red deposits, making them stand out even more. The idea of a world painted in sulfur may sound alien, but in some ways it connects to Earth's past. Billions of years ago, Earth's early atmosphere was rich in volcanic gases, including sulfur compounds. Vast eruptions may have spread similar deposits, though water and erosion have long since erased them. Io preserves a glimpse of what such worlds might have looked like, not in the distant past but in the present. Its sulfur-rich surface is a living laboratory, showing us processes that may once have shaped Earth and may still shape other planets. For scientists, the colours of Io are more than just beautiful. They are clues to its chemistry and activity. By analysing the light reflected from the surface, researchers can determine the composition of different regions, tracking how sulfur and sulfur dioxide are distributed. These observations reveal patterns linked to volcanic activity, showing where eruptions are most intense and how the surface changes over time. The colours are not just decoration, they are data telling the story of Io's ongoing transformation. But beyond the science, the visual impression remains powerful. Io is not simply another grey rock in space. It is a vivid, dynamic world, glowing with the colours of chemistry and heat. Its painted surface makes it stand out even among the strange landscapes of the outer solar system. Europa's icy fractures are beautiful. Titan's methane lakes are haunting. Enceladus's plumes are delicate. But Io's sulfur plains are startling in their intensity. They remind us that beauty in the cosmos can take many forms, some familiar, others utterly alien. The sulfur also contributes to Io's role in Jupiter's environment. As plumes release gas, sulfur dioxide escapes into space, feeding the plasma torus around the planet. This torus glows in ultraviolet light, another form of painting, not on the surface but in the space surrounding Jupiter. Io's sulfur does not stay confined to the moon. It becomes part of a larger system, spreading colour and energy outward. The painted landscape of Io is therefore only part of the story. The true canvas extends all the way around Jupiter, a halo of sulfur particles born from Io's eruptions. Standing on Earth, looking through a telescope, Io does not reveal these details. It appears as a small dot, faintly coloured, close to the brilliance of Jupiter. But knowing what lies beneath that dot changes the perspective. That tiny speck is not uniform or dull. It is a world painted in vivid hues, repainted constantly by forces we cannot hear but can see from afar. Its surface is both a work of art and a record of geological violence, a reminder that even the smallest moons can surprise us with their complexity. The longer you reflect on Io's surface, the more you realise how fleeting each detail must be. The ring of red around a plume may last only until the next eruption buries it. A bright frost field may vanish under sunlight or sublimate into the thin atmosphere. A dark lava plain may cool and fade, only to be covered again by fresh flows. The painting is never finished, never final. It is an endless process, a canvas that erases itself even as it creates new patterns. This impermanence is part of what makes Io so fascinating. Unlike the ancient scars of the Moon or Mars, Io's face is always new, always young, always changing. The sulfur also influences the experience of imagining life there. To us, sulfur is often associated with toxicity, with unpleasant smells, with inhospitable environments. On Io, it dominates so completely that the idea of life seems unlikely. The ground is coated with chemicals that are harsh and reactive. The atmosphere is thin, made mostly of sulfur dioxide, unbreathable and unstable. Yet the very extremeness of it teaches us something important, that worlds can be utterly different from Earth and still be dynamic, still be geologically alive. The sulfur may repel us, but it also fascinates us, because it shows how varied planetary surfaces can be. From a purely visual perspective, Io is breathtaking, The yellows and reds shine in the sunlight, creating a warmth that contrasts with the cold of space. The whites and blacks add contrast, highlighting the variety of deposits. The rings of plumes, the jagged mountains, the smooth plains, all of it comes together into a mosaic that is more vivid than anything else we have found in the solar system. To call it painted is no exaggeration. It truly looks like the work of an unseen artist, using sulfur instead of pigment, volcanoes instead of brushes, eruptions instead of strokes. And so Io continues, painting itself with every eruption, layering colours over colours, erasing old patterns and creating new ones. Its surface is never still, never plain, always shifting, always vivid. Each plume adds another circle, each flow adds another scar, each frost adds another patch of white. The sulfur is not just a substance, it is the medium of Io's identity, the reason it looks so strange, the reason it captivates us. When people imagine mountains on other worlds, they often picture them as smaller cousins of the ranges on Earth, quiet ridges rising gently from flat plains, weathered by time and erosion. But Io does not follow such familiar rules. On this small volcanic moon, mountains rise that dwarf the tallest peaks on Earth, reaching staggering heights of more than 15 kilometers above the plains around them. To put that into perspective, Mount Everest, Earth's highest peak above sea level, stands at just under 9 kilometers. On Io, mountains nearly twice that size are not rare exceptions, but part of the natural order. These mountains are not shaped in the way Earth's ranges are shaped. On our planet, mountains form where tectonic plates collide, pushing up folds of rock over millions of years. They are sculpted by wind, rain, ice and rivers, worn down even as they rise. On Io there is no thick atmosphere, no rain, no ice, no rivers. There are no tectonic plates drifting across the surface. The mountains of Io rise through entirely different forces, forces tied to the same restlessness that fuels its volcanoes. They are blocks of crust that have been uplifted, tilted and broken under immense stresses, created by the constant flexing of Io's surface. When scientists first saw them in images from Voyager, they were astonished. Jagged peaks and massive plateaus jutted out of the sulfur plains, sheer cliffs rising higher than anything on Earth. Some mountains seemed to stand alone, isolated and solitary, not part of chains but like enormous monoliths scattered across the surface. Others appeared fractured, broken and slumping, their sides collapsing under their own weight. The sight was unlike anything on Earth or the Moon. These were mountains born of stress, not of collision, mountains created in a world with no weather but endless upheaval. To imagine standing at the base of one of these mountains is to picture a landscape both alien and overwhelming. The plain beneath your feet might be coated in sulfur frost, pale yellow and brittle. Ahead, the ground rises abruptly, a cliff face stretching kilometers into the black sky. The slope is jagged and sharp, with no softening from erosion. Blocks of rock may have tumbled down the face, forming chaotic piles at the base. From that vantage, the sheer scale would be difficult to comprehend. With no atmosphere to blur the distance, every detail would appear stark, the cliffs towering with impossible clarity. Looking upward, you might feel as if the mountain were about to fall over you, its height more than double that of the tallest peaks on Earth. These mountains form because Io's crust is under constant strain. The tidal heating that melts the interior also stresses the outer shell. As magma pushes upward, as the crust flexes with each orbit, blocks of rock are shoved aside, tilted upward and fractured. Over time, some of these blocks are pushed so high that they become mountains taller than Everest. But unlike Earth's mountains, which are connected to vast tectonic systems, Io's are unstable. They are prone to collapse, their slopes fractured, their foundations undermined by the very processes that raised them. Landslides are common, sometimes covering areas the size of entire cities. The mountains are temporary monuments to stress, destined eventually to crumble and be buried beneath lava flows. The distribution of mountains across Io tells part of its story. They are not clustered in neat ranges but scattered, often near volcanic regions but not always directly connected to them. Some rise near lava plains, others near plume deposits, others in regions that seem otherwise quiet. This randomness reflects the chaotic way stresses are distributed in Io's crust. There is no single pattern, no repeating chain. Each mountain is an individual, a solitary peak born of local forces, rising and falling on its own timescale. This individuality adds to their strangeness, making them feel less like ranges and more like scattered monuments across a restless plain. The composition of these mountains is thought to be silicate rock, stronger and denser than the sulfur plains that coat much of the surface. That strength is why they can rise so high without immediately collapsing. But even strong rock cannot withstand the constant upheaval of Io forever. Over time, as eruptions spread fresh lava across the landscape, as new stresses tilt the crust, old mountains weaken. They may slump, fracture, and collapse, their remains buried beneath younger deposits. This cycle ensures that even Io's tallest peaks are temporary, just like its plains and flows. On Io, nothing is permanent. One of the largest known mountains on Io is Busol Montes, a vast irregular complex that rises more than 17 kilometers at its tallest point. To compare, that is nearly twice the height of Everest, rising sheer and massive above the plains. Its cliffs are steep, its flanks fractured, evidence of landslides that have torn away portions of its slopes. From orbit, it appears as a dark, angular shape, its shadow stretching far across the surface. Features like this remind us just how extreme Io's geology can be. It is not only the most volcanic body in the solar system, but also home to some of the most dramatic mountains. The sheer cliffs of Io's mountains also highlight another difference from Earth. With no atmosphere, there is no erosion by wind or rain. The shapes we see are sharp and angular, unsoftened by time. On Earth, even the highest peaks are gradually worn smooth by glaciers, rivers, and weather. On Io, the absence of such forces preserves every jagged edge. The mountains stand raw and stark, their features unblurred, their fractures exposed. The effect is one of stark beauty, a world where landscapes are drawn in sharp lines rather than softened curves. These towering peaks also add to the hazards of Io's surface. For any future explorers, they would be immense obstacles, their cliffs unclimbable, their slopes unstable. Landslides could occur without warning, triggered by the same stresses that built the mountains. Combined with the constant volcanic activity, the mountains make Io one of the most treacherous surfaces in the solar system, yet their very danger is part of their fascination. They are symbols of the forces at work, monuments to the stress and heat that define Io's nature. From a distance, Io's mountains are part of its strange painted landscape. Their dark slopes stand out against the bright sulfur plains, their shadows stretching long across the surface. They break up the otherwise smooth expanses, adding contrast and variety. In images from spacecraft, they look like scars, raised blocks that tilt the surface into dramatic relief. They remind us that Io is not just a world of plains and flows, but one of towering heights and deep valleys, a world where extremes coexist side by side. The study of Io's mountains helps scientists understand more about its crust and interior. By examining their shapes, their heights, and their distribution, researchers can infer the thickness of the crust, the stresses at work, and the processes that create them. The fact that such tall mountains exist suggests that Io's crust is strong enough to support them, at least temporarily, despite the constant heating. This strength may come from silicate rock underlying the sulfur deposits, rock that resists collapse even under strain. Yet the frequent landslides show that this strength is not unlimited. The mountains are temporary, and their eventual collapse is inevitable. The mountains also connect Io to broader questions about planetary geology. They show us that even in the absence of tectonic plates, mountains can rise through other processes. They demonstrate how tidal heating and volcanic activity can create stresses strong enough to shape landscapes in dramatic ways. They also remind us that not all mountains need to be part of ranges. On Io, they stand alone, isolated peaks scattered across a volcanic plain. This challenges our Earth-centered view of what mountains should look like, expanding our sense of geological possibilities. If you imagine drifting across Io in orbit, looking down on its surface, the mountains would be some of the most striking features. They would cast long shadows across the plains, their jagged forms stark against the smoother lava flows. From that vantage you could see how they rise abruptly, how they stand solitary, how they dominate the landscape around them. You could see the fractures in their slopes, the evidence of landslides, the contrast between their dark rock and the bright sulfur around them. It would be a view both alien and beautiful, a reminder of how diverse and extreme planetary surfaces can be, and yet even these mountains are temporary. Like everything else on Io, they are subject to the cycle of creation and destruction. They rise under stress, fracture under strain, collapse under gravity, and are buried under lava. In time, new mountains will rise elsewhere, and the old ones will vanish. The cycle never ends, just as the eruptions never end, just as the tides never stop. Io's mountains are monuments not to permanence but to change, to the forces that keep the moon alive with motion. To think of mountains taller than Everest on a moon smaller than Earth's is to appreciate the extremes of Io. It is a world that pushes boundaries, that defies expectations, that refuses to be ordinary. Its mountains are part of that story, standing as stark reminders of the stresses within, the heat below, the violence above. They add vertical drama to a world already defined by horizontal chaos, making Io not only the most volcanic moon, but also one of the most mountainous. If the mountains of Io rise higher than anything on Earth, stark and jagged against the sulfur plains, the lakes that lie scattered across its surface offer an equally extraordinary sight. They are not lakes of water, nor seas of ice, nor gentle pools reflecting a blue sky. Instead, they are vast expanses of molten rock, glowing from within, shimmering in colours that seem impossible for a natural world. These are lakes of lava, some stretching for hundreds of kilometres, restless and shifting, burning with heat so intense that their light is visible across space. On Earth, lava lakes exist in only a handful of places. The most famous are in places like Kilauea in Hawaii or Mount Nyiragongo in the Congo. They're rare, fleeting, often unstable, forming for a time before cooling or erupting away. Standing near them, one can see molten rock churning and bubbling, its surface crust breaking and reforming as glowing magma pushes upward. On Io, however, lava lakes are not rare curiosities. They are central features of the landscape, vast and persistent, fueled by the endless energy of tidal heating. Where Earth offers a handful of examples, Io offers dozens, each larger, hotter and more active than any on our planet. Perhaps the most famous of Io's lakes is Loki Patera, a gigantic volcanic depression more than 200 kilometres across. If placed on Earth, it would dwarf entire countries. Its surface is a restless mosaic of dark crust and glowing cracks, constantly overturning as fresh lava wells up from below. From orbit, Loki appears to brighten and dim in cycles, as though breathing, a sign of the continual renewal of its surface. This brightening is so powerful that astronomers can detect it even from Earth using infrared telescopes. Loki alone releases more heat than all the volcanoes on Earth combined. It is a place where the concept of scale loses its usual meaning, where a single feature on a small moon outshines the entire volcanic activity of our own planet. The light from these lakes is not like firelight on Earth. In the vacuum of Io's thin atmosphere, there is no smoke, no flicker of flames, no sound. Instead, the glow is pure, steady and unfiltered, radiating from cracks and openings in the cooling crust. Fresh lava shines orange or even white hot, while older crust darkens to black as it solidifies. The result is a shimmering surface of contrasting tones, glowing veins crisscrossing dark plates, a restless patchwork of heat and colour. To an observer, it might resemble molten metal or stained glass lit from beneath, shifting and reforming with every moment. The chemistry of Io's lava lakes adds to their strangeness. Some eruptions are so hot that they must involve ultramafic lavas, rich in magnesium and iron, similar to those that shaped Earth billions of years ago but absent from modern volcanism. These lavas can reach temperatures exceeding 1600 degrees Celsius, far hotter than typical eruptions on Earth. At such temperatures, the light emitted would be brilliant, glowing in yellows and whites, far brighter than the duller reds of Earth's basaltic lavas. Other lakes may involve sulfur compounds which melt and boil at much lower temperatures, producing glowing pools of yellow or orange that shift rapidly as they vaporize. Together, these variations create lakes that glow in alien colors, unlike anything seen on our own planet. If you could hover above one of these lakes, the view would be mesmerizing. You would see vast rafts of solid crust, dark and jagged, drifting across a glowing sea of molten rock. Cracks would open suddenly, spilling fresh lava into view, glowing brightly before cooling again. The entire surface would appear alive, shifting constantly, never still. The scale would dwarf anything on Earth. What might seem like small cracks or flows from orbit would in reality be kilometers across, wide enough to swallow entire cities. The silence would be profound, but the sight overwhelming, a spectacle of fire on a scale beyond imagination. The persistence of Io's lava lakes is another remarkable feature. On Earth, lava lakes often disappear after months or years, drained or cooled by changes in activity. On Io, some have lasted for decades, maintained by the unceasing energy of tidal heating. Loki Patera, for example, has been active for as long as we have been observing it, cycling through phases of brightening and dimming without ever truly falling silent. This persistence makes Io unique. It is a world where molten lakes are not temporary, but permanent fixtures, part of the landscape for centuries at a time. From a scientific perspective, these lakes are invaluable. They provide direct evidence of Io's internal heat, its composition and its activity. By studying their brightness and cycles, scientists can infer the processes occurring beneath the surface, the way magma wells up, the way crust forms and sinks, the way heat is distributed. They also provide a glimpse into Earth's past, when ultramafic lavas may have been common, shaping continents and oceans in the planet's earliest days. In this sense, Io is not just another moon, but a time machine, showing us processes long vanished from our world. The lakes also contribute to Io's role in the Jovian system. The gases and particles released by their activity escape into space, adding to the plasma torus around Jupiter. This interaction links the fiery surface of Io directly to the giant planet's magnetic field, creating auroras that shine even from Earth. In this way, the glowing lakes of Io not only shape its surface, but also light up the skies of its parent planet. They are part of a chain of influence that extends far beyond the moon itself. Visually, the lakes are among the most spectacular sights in the solar system. Imagine a landscape of black plains and sulfur frost, broken suddenly by a vast depression glowing with molten light. The contrast would be stark and beautiful, alien and yet familiar in its resemblance to fire. From orbit, the glow would be unmistakable, shining through the darkness like an ember in the night. To see it in person would be to witness the raw energy of a world forever in motion, a reminder that the cosmos is not only cold and still, but also alive with heat and change. The names of Io's lakes reflect their drama. Loki Patera, Pele Patera, and many others are named after gods and goddesses of fire from mythologies around the world. The names are fitting, evoking the power and intensity of the features. They remind us that across cultures, Fire has always been a symbol of creation and destruction, of danger and beauty. On Io, these symbols take physical form, vast lakes of fire glowing against the silence of space. The scale of Io's lava lakes also challenges our sense of proportion. On Earth, even the largest lava lake is only a few kilometers across. On Io, they can be hundreds of kilometers wide, large enough to be entire countries if placed on our planet. The sheer size makes them difficult to grasp. They are not just geological features, but entire worlds within a world, landscapes of their own, with mountains, islands, and flows all contained within their boundaries. Each one is a microcosm of Io's activity, a place where the dance of tides and fire is concentrated and made visible. From an artistic perspective, the lakes of Io might be imagined as alien jewels, glowing within a light, set against a dark and barren plain. They are sources of contrast and wonder, highlighting the strange beauty of a world so different from our own. From a scientific perspective, they are laboratories, windows into processes we cannot reproduce on Earth. From a human perspective, they are simply awe-inspiring, reminders of the scale and power of nature beyond our planet. The glow of Io's lakes also reminds us of impermanence. Though they persist for decades, even centuries, they are not eternal. They may shift, drain, or change with time. New lakes may form, old ones may vanish, just as new mountains rise and old ones crumble. The surface of Io is never fixed, never permanent. The glowing lakes are part of that cycle, symbols of both persistence and change, constancy and renewal. As you picture them, glowing silently in the darkness, imagine how they would look from a spacecraft drifting above. The black plains stretching out, the sulfur frost glinting faintly, and then, suddenly, a vast pool of light, shimmering with molten colours. The scale would be difficult to comprehend, the silence profound, the beauty overwhelming. It is a vision that few have seen directly, but one that defines Io as surely as its volcanoes, its mountains, or its sulfur plains. When we imagine an atmosphere, we think of the thick blanket of air around Earth, the swirling winds of Jupiter, or the golden haze of Titan. Atmospheres are usually permanent and enveloping, great cushions of gas that define the environment of a planet or moon. But Io does not follow that pattern. Its atmosphere is not thick, not stable, not protective. Instead, it is thin, fleeting and fragile, so tenuous that it would collapse without the constant support of volcanic eruptions and sunlight. It is more like a veil than a blanket, more like a breath than a shield. Yet even in its fragility, Io's atmosphere adds to its uniqueness, playing a small but vital role in the restless life of this volcanic world. The main component of Io's atmosphere is sulfur dioxide, a gas released in vast amounts by volcanic eruptions. When plumes rise hundreds of kilometers above the surface, they eject not only particles of sulfur that fall back as frost, but also clouds of sulfur dioxide gas that spread across the moon. Some of this gas escapes into space, feeding Jupiter's magnetosphere, while the rest forms a thin and temporary atmosphere around Io. This atmosphere is not stable like Earth's. Instead, it constantly collapses and reforms, waxing and waning in step with Io's day and night, and with the activity of its volcanoes. During the daytime, sunlight warms the surface, causing frozen sulfur dioxide to sublimate directly from solid into gas. The result is a thin layer of atmosphere clinging faintly to the surface, thickest near active volcanic regions. At night, when the temperature drops, this gas condenses again, freezing back onto the surface as frost. In effect, Io's atmosphere disappears each night, only to reappear when the sun returns. It is a cycle unlike anything on Earth, an atmosphere that comes and goes with the rising and setting of the sun, as fragile as morning dew on our planet but made of sulfur frost instead of water. The pressure of Io's atmosphere is minuscule compared to Earth's. Standing on its surface, you would find it more than 1 billion times thinner than what we breathe here. It would not carry sound. It would not scatter light into a blue sky. It would not shield you from radiation. The sky would be black even at noon, with the sun shining harshly and Jupiter looming overhead. The thin gas would cling close to the ground, barely present, invisible except for the faintest glimmers of light when observed from orbit. To walk through it would be like walking through nothing at all. Yet fragile as it is, the atmosphere of Io plays an important role in connecting the surface to space. Every volcanic eruption pumps new gas into it, replenishing it and extending its reach. The most active volcanoes, such as Pele, generate local atmospheres around their plumes, thick enough in places to drive winds that spread frost across the plains. These localized bubbles of gas merge into the global veil, thickening it for a time before it collapses again. The atmosphere, thin as it is therefore a direct expression of Io's volcanic activity. Without the volcanoes, it would vanish altogether. The interaction between Io's atmosphere and Jupiter's magnetic field adds another layer of complexity. As the Moon moves through the giant planet's powerful magnetosphere, the thin gas becomes ionized, stripped of electrons by the charged particles that sweep past. These ions are carried away, forming part of the plasma torus that encircles Jupiter. In this way, Io's atmosphere does not stay confined to the Moon. It leaks into space, feeding energy into a system much larger than itself. The plasma torus glows in ultraviolet light, a giant invisible ring powered by Io's fragile veil of gas. The thinness of Io's atmosphere also means that conditions on the surface are extreme. Without a protective layer of gas, there is no moderation of temperature. In the sunlight, the surface can reach more than minus 130 degrees Celsius. In shadow, it can plunge much lower. The lack of atmospheric pressure means that liquid water cannot exist. It would instantly boil away. Even sulfur dioxide, which makes up the atmosphere, is unstable, freezing and thawing with each cycle of day and night. The surface is a place of extremes, unmoderated by air, unshielded from radiation, unsoftened by weather. To imagine standing on Io under this fleeting atmosphere is to imagine silence and starkness. The sky would be black, Jupiter massive above the horizon. The ground would crunch with sulfur frost, and faint wisps of gas might rise from nearby vents. You would not feel the atmosphere around you, because it is too thin to notice. You would not hear any sound, because there is no medium to carry it. The only signs of the atmosphere would be subtle, the frost forming and disappearing, the glow of plumes, the faint haze that forms around the horizon in certain conditions. It is an atmosphere so delicate that it could almost be missed, and yet without it, Io's connection to Jupiter would be incomplete. The day-night cycle of Io's atmosphere is one of its most fascinating features. On Earth, our atmosphere is stable, its gases bound by gravity, cycling through weather patterns that shift but never vanish. On Io, the atmosphere itself breathes in and out with the sun, condensing at night, sublimating by day. It is as though the Moon inhales and exhales in sulfur, its breath timed to the rising and setting of the light. This rhythm adds to Io's strangeness, making it a world where even the air is temporary, where nothing is permanent, not even the veil of gas that surrounds it. Scientists studying Io's atmosphere use careful observations of how light passes through it. When Io passes in front of Jupiter, the thin gas absorbs certain wavelengths, revealing its composition. When sunlight reflects off the frost, it shows how much sulfur dioxide is present. Spacecraft flying past have measured the atmosphere directly, finding that its density changes not only with day and night, but also with volcanic activity. During major eruptions, the atmosphere thickens noticeably, becoming hundreds of times denser than usual in localized regions. But even then, it remains fragile, still far thinner than the best vacuums we can create on Earth. The fragility of Io's atmosphere also makes it unstable in the long term. Gas constantly escapes into space, carried away by Jupiter's magnetosphere. New eruptions replace it, but the balance is delicate. If Io's volcanoes were ever to quiet, the atmosphere would collapse entirely, leaving only frost and vacuum. But as long as the tidal heating continues, as long as eruptions persist, the atmosphere will remain, waxing and waning with the sun, never thick but never entirely absent. The influence of Io's atmosphere extends beyond the moon itself. As ions escape into space, they flow along Jupiter's magnetic field lines, connecting Io directly to the giant planet. This connection creates electric currents that generate auroras at Jupiter's poles. In this sense, Io's fleeting atmosphere helps power lights on a planet more than 1,000 times its size. The veil of gas may be fragile, but its consequences are vast, linking a tiny moon to the largest planet in the solar system in a cycle of energy and light. The atmosphere also contributes to the strange beauty of Io's surface. When plumes erupt, their gases rise high into space, spreading in arcs before falling back as frost. These arcs can form hazy halos around volcanic vents, faint glows visible even in the thin sunlight. Around some volcanoes, frost deposits create bright rings, marking where the atmosphere was briefly thicker. These patterns are visible from orbit, adding to the painted appearance of Io's landscape. The atmosphere may be thin, but it leaves visible traces, marking the moon's surface with circles and patches that record its fleeting presence. From a human perspective, Io's atmosphere is inhospitable, toxic, and useless for life. It cannot be breathed, it cannot shield, it cannot warm. Yet from a scientific perspective, it is rich with information. It tells us how Io's surface interacts with its volcanoes, how the gases cycle between solid and vapor, how the moon connects to Jupiter's magnetosphere. It is a reminder that even the thinnest veil of gas can shape the character of a world, linking its geology to its space environment in ways that are both subtle and profound. When you imagine Io drifting around Jupiter, imagine also this fragile breath of gas clinging faintly to the surface, vanishing and reappearing with the sun. Imagine it glowing faintly around volcanic plumes, streaming away into space, feeding a torus of plasma that encircles the giant planet. Imagine how delicate it is, how temporary, how fragile, and yet how essential to the identity of Io. The thin, fleeting atmosphere may not be as dramatic as the mountains or as spectacular as the lava lakes, but it is part of the same restless system, another way in which Io refuses to be ordinary. The eruptions on Io are unlike anything else in the solar system. On Earth, volcanic plumes can rise high into the atmosphere, spreading ash and gas for hundreds of kilometers, but they remain bound by the sky. They fade into winds, they settle back onto the surface, they remain within the reach of gravity and air. On Io, there is no thick sky to contain them, no atmosphere to slow their climb. When a volcano erupts here, its plumes do not simply rise into air, they burst directly into the vacuum of space, soaring hundreds of kilometers above the surface, creating arcs that can stretch across the entire horizon of the moon. The first time these plumes were observed was during the Voyager 1 flyby in 1979. Scientists had expected to see craters, perhaps plains of ice, maybe a world scarred by impacts like other moons of Jupiter. Instead, the cameras captured towering eruptions, great fountains of sulfur dioxide climbing more than 300 kilometers into space. To see such activity on a distant moon was astonishing enough, but the sheer scale was beyond what anyone had imagined. Some of these plumes were larger than entire planets, visible even against the bright backdrop of Jupiter. They were eruptions that did not merely reshape the surface, they reached out and touched space itself. These plumes form because of the unique combination of Io's geology and its thin atmosphere. On Earth, explosive eruptions are driven by water vapor and gases trapped in magma. When pressure builds, they burst forth, propelling ash and rock into the air. On Io, the main gas is sulfur dioxide stored beneath the crust and released during eruptions. When it escapes into the vacuum, it expands violently, unrestrained by air pressure, creating vast fountains that arc across the sky. Because there is no atmosphere to slow them, the particles can rise much higher than they ever could on Earth. The result is a spectacle of scale unmatched anywhere else we know. One of the most famous examples is the volcano Pele. When Voyager 1 flew past, it caught an image of a plume rising more than 300 kilometers above the surface, its deposits forming a red ring more than 200 kilometers across. That single eruption was so large that its effects covered nearly a fifth of the moon. The red colour came from sulfur compounds altered by the heat of the eruption, leaving behind a vivid scar on the surface. Pele's plume remains one of the most iconic sights in planetary science, a reminder that Io is not only volcanic, but explosively so, on a scale beyond Earth's imagination. Another extraordinary example is Tvashtar, a volcano that has produced some of the tallest plumes ever observed on Io. During the Galileo mission, its eruption sent fountains of gas and dust rising more than 400 kilometers high, reaching well into space. From orbit, the plumes appeared as bright umbrellas spreading above the horizon, faintly glowing in the sunlight. The deposits they left behind formed enormous rings, marking the reach of the eruption. To see such a fountain from the surface would be to witness a wall of material arching silently into space, stretching across the sky, dwarfing any feature of the landscape below. The physics of these eruptions is fascinating. When sulfur dioxide gas expands into the vacuum, it cools rapidly, freezing into tiny crystals that fall back to the surface as frost. This process creates the bright white rings around plume vents, visible in spacecraft images as circular patterns hundreds of kilometers wide. These rings are not permanent, as new eruptions bury or erase them, but they are striking while they last. They are the footprints of eruptions that reached into space, records of fountains so immense that they painted entire regions of the surface. The plumes also demonstrate how Io's activity connects directly to space. On Earth, volcanic plumes can alter the atmosphere, cooling the climate for months or years. On Io, they do something even more dramatic. They add material directly to Jupiter's magnetosphere. The gas that escapes from plumes does not remain bound to the moon. Instead, it is swept up by the giant planet's magnetic field, forming the Io plasma torus, a vast ring of charged particles that encircles Jupiter. This plasma interacts with the planet's field, creating auroras and currents that connect back to Io itself. In this sense, every eruption on Io is not just a local event, but a system-wide phenomenon, affecting the environment of a planet more than 1,000 times its size. From a human perspective, to imagine witnessing one of these eruptions is to imagine silence and scale. On Earth, a volcanic eruption is deafening, a roar of gas and rock tearing through the air. On Io, there would be no sound, no roar, no echo. The plume would rise in utter silence, arching above the horizon, expanding into space. The only sense would be visual, a vast glowing fountain, particles catching the sunlight, falling back in a graceful arc to coat the ground. It would be a sight of pure motion without noise, a spectacle of scale without sound. The silence would make it even more surreal, more alien, more unlike anything on Earth. The eruptions that touch space are also reminders of Io's relentless energy. They are not rare or occasional but constant, occurring at dozens of sites across the moon. Some plumes are small, rising only a few tens of kilometers. Others are vast, reaching hundreds of kilometers high. At any given time, multiple eruptions are active, their plumes overlapping, their deposits merging. The surface is never still, never quiet. Even as one eruption fades, another begins elsewhere, continuing the cycle of creation and destruction. The scale of these eruptions also challenges our understanding of planetary activity. On Earth, even the most powerful eruptions are limited by the atmosphere, by gravity, by the availability of water vapor. On Io, those limits do not exist. Gravity is weaker, the atmosphere is negligible, the gases involved expand freely into space. The result is eruptions that defy comparison, eruptions that are literally planetary in scale. They remind us that volcanism is not confined to the conditions we know, that in different environments it can take on entirely new forms. Scientists studying these plumes have learned much about Io's interior and its interaction with Jupiter. By analysing their composition, they can determine the gases involved, the temperatures of the eruptions, the sources of the material. By tracking their heights and distributions, they can infer the pressures beneath the crust and the processes that drive them. The plumes are not just spectacular sights, they are data, evidence of the forces at work inside the moon. They are windows into Io's geology, showing us directly how tides and heat translate into activity. The plumes also remind us of the impermanence of Io's surface. Each eruption repaints the landscape, covering old deposits with new frost, erasing craters, burying plains. The bright rings of deposits are visible for a time, but eventually they are overwritten by the next eruption. The surface of Io is therefore not a permanent record, but a constantly changing canvas, renewed again and again by eruptions that reach into space. The plumes are both destructive and creative, erasing the old while creating the new, a cycle that has no end as long as the tidal heating continues. From orbit, the sight of a plume is breathtaking. Imagine a spacecraft drifting above Io, its cameras capturing a great umbrella of gas spreading across the black sky, the surface below coated in vivid colours. Imagine the glow of fresh deposits, the stark contrast between bright frost and dark lava. Imagine the scale so vast that the plume covers entire regions, so high that it rivals the size of the moon itself. These are not eruptions confined to the ground. They are eruptions that shape the space around Io, eruptions that touch the stars. The fact that these eruptions were first seen in 1979 is itself a reminder of how recent our understanding of Io is. For centuries, it was only a point of light, a companion of Jupiter, a curiosity in a telescope. In a single flyby, Voyager revealed it as the most volcanic world in the solar system, a place of eruptions so immense that they reach beyond the surface into space. That discovery transformed not only our view of Io, but our understanding of planetary activity itself. It showed us that volcanism is not confined to Earth, that it can be far more extreme, far more spectacular, in places we never expected. And so Io continues, erupting into space, painting its surface, feeding Jupiter's magnetosphere, shaping its environment in ways that reach far beyond the moon itself. Each plume is a reminder of the power of tides, the inevitability of heating, the scale of forces at work. Each plume is also a spectacle, a fountain of gas and frost reaching into the vacuum, arching gracefully across the sky. They are eruptions that outshine Earth's, eruptions that reshape a world, eruptions that touch space itself. When we think of auroras, our minds turn first to Earth, to the shimmering curtains of light that dance across polar skies when solar winds stir our magnetic field. Those green and red displays are among the most beautiful phenomena our planet offers, weaving light into darkness, silent and ethereal. But auroras are not unique to Earth. They exist wherever magnetic fields and charged particles meet, and around Jupiter auroras burn brighter, more powerful than any on our planet, fueled not only by the sun but by the activity of its moons. At the centre of that story is Io, whose constant eruptions send material into space, linking a small volcanic world to the glowing crown of the largest planet in the solar system. Every time Io erupts, sulfur dioxide gas escapes into space, forming a tenuous cloud around the moon. Much of it settles back, freezing into frost, but a portion escapes Io's weak gravity. Jupiter's immense magnetic field sweeps past Io, capturing these particles and ionizing them, stripping electrons away and turning neutral gas into plasma. This plasma is not scattered randomly, but forms a torus, a giant ring of charged particles that encircles Jupiter along Io's orbit. The torus glows in ultraviolet light, invisible to our eyes but striking in spacecraft images, a luminous halo born from volcanic eruptions far below. As Jupiter's magnetic field rotates, it drags this plasma with it, carrying particles along its lines of force. Some of these particles are funneled into the planet's upper atmosphere, striking atoms and molecules and exciting them into glowing. The result is auroras at Jupiter's poles, immense rings of light thousands of kilometers wide, burning in ultraviolet and visible wavelengths. They are the most powerful auroras in the solar system, brighter than anything seen on Earth, fueled not only by solar wind but by a moon barely a fraction the size of our own. The connection between Io and these auroras is direct and constant. As Io orbits, it creates an electric current along Jupiter's magnetic field lines, a flow of energy known as the Io flux tube. This current carries charged particles from the moon to the planet, linking them in a circuit of light and power. Where the flux tube meets Jupiter's atmosphere, it creates a bright spot in the aurora, a glowing mark that follows Io as it moves. In effect, the moon paints its presence onto the planet, a moving beacon of light that reveals the invisible link between them. To grasp the scale of this phenomenon, imagine Earth's northern lights magnified hundreds of times, stretching not across a continent but across a planet 11 times wider than Earth. Imagine that instead of solar wind, the main fuel is a single moon, ejecting material into space that then cascades down as light onto its parent. Imagine auroras so bright that they shine in wavelengths invisible to human eyes, captured only by instruments but burning with more energy than any natural light on Earth. This is what Io creates around Jupiter, a display of power and beauty on a scale far beyond anything we can experience here. For a spacecraft orbiting Jupiter, these auroras are breathtaking. The Juno mission has captured images of them glowing at the poles, immense ovals of light that never fade. They are not transient like Earth's auroras, appearing and disappearing with the solar wind. They are permanent, continuous, sustained by Io's endless eruptions and Jupiter's unyielding magnetic field. To orbit Jupiter is to orbit a world crowned by constant aurora, a world where light never stops dancing at the poles, a world where a small moon keeps the heavens glowing. The role of Io in this system is a reminder that moons are not passive. For a long time, astronomers imagined moons as quiet companions, circling their planets but contributing little beyond their presence. Io proves otherwise. Its activity feeds Jupiter's magnetosphere, alters its radiation environment, and fuels its auroras. It is not a passive satellite but an active participant, shaping the space around its planet in ways that no other moon in the solar system does. Its eruptions may begin on the surface, but their influence reaches far into space, all the way to the poles of Jupiter, where they paint light into darkness. From Earth, these auroras are too distant to see with the naked eye. Our telescopes can detect them in ultraviolet, recording the glow that Io helps create. But knowing they are there changes the way we see the system. That tiny dot of light near Jupiter, that restless volcanic moon, is powerful enough to create phenomena visible across millions of kilometers, phenomena that shape the environment of the largest planet in the solar system. It is a reminder that size alone does not dictate influence, that even small worlds can leave marks on giants. The auroras themselves are not uniform. The spot created by Io's flux tube is only one part of a much larger display. Surrounding it are arcs and ovals that shift with the rotation of Jupiter and the flow of plasma. Some brighten when eruptions on Io intensify, evidence of the direct link between the moon's activity and the planet's glow. Others flicker with variations in the magnetic field, responding to subtle changes in the flow of particles. Together they form a living light show, dynamic and ever-changing, powered by a moon that never rests. For scientists, these auroras are not only beautiful but informative. By studying their brightness and structure, researchers can learn about the interactions between Io and Jupiter, the composition of the plasma torus, the strength and shape of the magnetic field. The auroras act as a kind of diagnostic tool, revealing processes invisible in other ways. They show us how energy flows in this system, how a moon can drive currents and lights across a planet far larger than itself. In this sense, the glow of aurora is both a spectacle and a message, a visible sign of invisible forces at work. To imagine standing on Io and looking up at Jupiter is to imagine seeing the auroras from another perspective. The planet would loom enormous in the sky, filling much of the horizon, its bands and storms swirling in slow motion. Near its poles, faint glows might be visible, though the human eye might not perceive them clearly. Yet to know that those glows are partly your doing, that the particles erupting from the surface beneath you are lighting up the planet above, is to feel the connection between moon and planet in a way that is almost tangible. It is a relationship written not only in gravity but in light, a bond expressed in auroras. The glow of aurora around Jupiter is among the most constant phenomena in the solar system. Unlike the transient flashes of comets or the shifting storms of Saturn, these auroras persist, day after day, year after year, as long as Io continues to erupt. They are a cosmic reminder of permanence within change, of light sustained by fire, of a system in balance even as it churns with violence. They link the surface of a small moon to the atmosphere of a giant planet, creating beauty from destruction, turning eruptions into light. And yet, for all their brightness, these auroras are only part of Io's influence. The particles escaping from the moon do not stop at Jupiter's poles. They spread across the magnetosphere, altering its currents, shaping its radiation belts, influencing the entire space environment of the Jovian system. Io's eruptions touch not only space, but the space around a giant planet, reshaping it in ways that continue to challenge our understanding. The auroras are the most visible sign, but they are only one aspect of a much larger story, a story of plasma and fields, of currents and forces, of a moon whose reach extends far beyond its size. To drift in orbit around Jupiter, watching its auroras flicker and burn, is to see the cosmos at its most interconnected. A moon and a planet, linked by fire and light, each shaping the other in ways both visible and invisible. Io's eruptions begin as heat beneath the crust, but they end as light in the sky of a giant planet. They are a cycle of transformation, energy passing from tides to fire, from fire to gas, from gas to plasma, from plasma to light. The glow of aurora around Jupiter is the final step in that cycle, the visible end of an invisible journey, the crown of a dance that stretches from the surface of a moon to the heart of a planet's magnetic field. For centuries, Io was little more than a faint point of light drifting near Jupiter, first seen through Galileo's telescope in the winter of 1610. In those early days, it was simply one of 4 dots, remarkable because they circled Jupiter instead of Earth, but otherwise silent and mysterious. For more than 3.5 centuries afterward, little changed. Telescopes grew stronger, astronomers charted its orbit, and hints of colour and brightness flickered at its surface, but the details remained hidden. It was not until the late 1970s that humanity finally came close enough to see Io for what it really was, and the spacecraft that revealed its secrets was Voyager. The Voyager program was among the most ambitious missions NASA had ever attempted. 2 spacecraft, Voyager 1 and Voyager 2, launched in 1977, destined for the outer solar system. Their paths were chosen carefully, timed for a rare planetary alignment that allowed them to visit Jupiter, Saturn, and beyond using the gravitational slingshot effect. Their cameras and instruments were designed to capture images of worlds that had never before been seen up close, turning points of light into real places. When Voyager 1 reached Jupiter in early 1979, one of its key targets was Io. Scientists expected Io to be like the Moon or Mercury, perhaps a rocky, cratered surface, maybe with patches of ice. Some speculated about differences, but no one imagined what they were about to see. As Voyager's cameras began sending back images, the first surprise was the lack of craters. Other moons of Jupiter were covered in them, scars from billions of years of impacts. But Io appeared smooth, bright, and strangely mottled, painted in yellows and reds. The absence of craters suggested a young surface constantly renewed. That alone was astonishing, but the biggest revelation came not from a still image, but from motion. As Voyager 1 approached, its navigation cameras captured something extraordinary. A plume rising from Io's surface, a great fountain of gas and particles arcing into space. At first, it seemed almost too strange to be real. Scientists had not expected to see activity on Io at all, much less a volcano erupting into space. Careful analysis confirmed it. Voyager had caught the first evidence of active volcanism beyond Earth. What was once thought of as a dead rock circling Jupiter was in fact the most volcanically active world in the solar system. The discovery was dramatic. In March 1979, scientists gathered at NASA to present the images to the world. They showed Io not as a barren moon, but as a world alive with fire, its surface reshaped constantly by eruptions. The plumes captured by Voyager were immense, hundreds of kilometers high, dwarfing anything on Earth. The deposits they left behind painted the surface in vivid colors, red and orange rings spreading across the plains. The images shocked even seasoned researchers who had spent their lives studying planets and moons but had never seen anything like this. Voyager 1 revealed at least 9 active volcanic plumes on Io during its flyby. Some were tall, arching hundreds of kilometers into space. Others were smaller, forming local deposits of frost and ash. The sheer number and scale proved that Io was not just active, but hyperactive, a world dominated by volcanic processes. These eruptions explained the lack of craters. The surface was constantly being repaved, burying old scars beneath new flows and deposits. Io's youth was not a mystery of chance, but a direct result of its restlessness. The details captured by Voyager's cameras were striking. The surface appeared mottled with bright patches of yellow and white, caused by sulfur dioxide frost. Dark regions marked fresh lava flows, still warm and glowing in infrared images. Red and orange rings surrounded plume sources, coloured by sulfur compounds altered by heat. The variety of colours was unlike anything else in the solar system, a palette more vivid than Mars, more alien than our moon. Io's surface looked painted, strange and surreal, and the knowledge that these colours were constantly shifting made it even more remarkable. The discovery of Io's volcanism also raised deeper questions. Where did the energy come from? How could a small moon, only slightly larger than Earth's own moon, produce more heat than all of Earth's volcanoes combined? The answer, as scientists pieced together, lay in tidal heating. Voyager's data helped confirm the theory that Io's orbit was kept eccentric by resonance with Europa and Ganymede, forcing the moon to flex under Jupiter's gravity. That flexing generated heat, enough to melt rock and drive eruptions. Io's fury was explained not as an accident but as the inevitable outcome of its orbital dance. Voyager 2 followed Voyager 1 later in 1979, offering additional views of Io. By then, some of the volcanic plumes seen by Voyager 1 had vanished, while others had appeared in different places. This confirmed that the activity was not static but dynamic, changing in real time. The surface seen by Voyager 2 was already different from that seen by Voyager 1, a vivid reminder that Io does not hold still long enough to preserve its own past. For planetary science, this was revolutionary. Until then, most bodies in the solar system had seemed ancient and static, shaped in the distant past but quiet now. Io was alive, a world where geology was not just history but ongoing. The Voyagers did more than reveal Io's volcanism. They also captured its interaction with Jupiter's magnetosphere. Instruments detected the plasma torus created by Io's eruptions, a ring of charged particles encircling Jupiter along Io's orbit. They observed the footprints of Io's influence on Jupiter's auroras, the glow of energy transferred from moon to planet. These findings expanded Io's significance, showing it was not only reshaped by Jupiter, but also reshaping its parent in return. A tiny moon had become a driver of planetary scale phenomena. The public reaction to Voyager's revelations was as dramatic as the science. Newspapers printed images of Io's colourful surface, describing it as the most bizarre world ever seen. Headlines spoke of volcanic eruptions larger than Mount Everest, of plumes taller than the Empire State Building stacked dozens of times. For the first time, the general public could see a world beyond Earth that was not simply cold and dead, but active and violent, alive with processes familiar yet magnified to extremes. Io became a symbol of discovery, a reminder that the solar system was far stranger than anyone had imagined. For scientists, the images of Io marked a turning point. Before Voyager, planetary geology had been largely comparative, using Earth as the model and fitting other worlds into that framework. After Voyager, it was clear that the solar system contained environments that defied expectations, that followed their own rules. Io was not Earth-like, nor Moon-like, nor Mars-like. It was something entirely different. The lesson was profound. We could not assume that other worlds would mirror our own. Each had its own story, its own processes, its own surprises. Voyager's legacy lives on in the way Io continues to be studied. The Galileo spacecraft in the 1990s, and later telescopes on Earth and in space, have built on Voyager's discoveries. But the first images remain iconic, the moment when a dot of light became a fiery world. The sight of plumes reaching into space, captured unexpectedly by Voyager's cameras, remains one of the great moments in planetary exploration. It was the first time we realized that volcanism could dominate a small moon. The first time we saw a world where eruptions outshone craters. The first time we glimpsed the full extent of Jupiter's influence on its moons. If you imagine watching those images come in for the first time, the sense of awe is easy to understand. For generations, Io had been a mystery. In a single moment, that mystery was shattered and replaced with wonder. The moon was not silent, but roaring with fire. It was not ancient and static, but young and dynamic. It was not simply another dot of light, but a world unlike any other. The Voyagers had revealed Io's secrets, and in doing so they had changed our understanding of what moons could be. When Voyager revealed Io's secrets in 1979, the world of planetary science was shaken. A small moon had turned out to be the most volcanically active body in the solar system, its surface painted in sulfur, its plumes touching space. But Voyager's flyby was brief, a momentary encounter, a snapshot rather than a sustained visit. Scientists were left with burning questions. How constant was Io's volcanism? How often did eruptions occur? How did its activity connect to Jupiter's magnetosphere? What forces shaped its mountains, its lakes of fire, its strange atmosphere? To answer these questions, another mission would be needed. Not a fleeting glimpse, but a prolonged exploration. That mission was Galileo. Launched in 1989 aboard the space shuttle Atlantis, Galileo's journey to Jupiter was long. Instead of a direct path, it took a winding route, using gravity assists from Venus and Earth to gain speed. For more than 6 years it travelled, a patient voyage through the inner solar system, past asteroids, and finally into the realm of the gas giant. In December 1995, Galileo entered orbit around Jupiter, becoming the first spacecraft to circle the giant planet. For nearly 8 years it remained there, looping again and again through the Jovian system, passing close to the moons, studying the magnetosphere, and sending back a flood of data. Among its many targets, Io was one of the most tantalizing. Galileo's instruments were designed for close observation: high-resolution cameras, infrared spectrometers, magnetometers, and plasma detectors. All were tuned to probe the mysteries of Jupiter and its moons. For Io, these instruments promised not just images, but measurements of heat, composition, and magnetic interactions. Unlike Voyager, which could only watch from a distance during a quick flyby, Galileo could linger, return, and watch changes unfold over time. Almost immediately, Galileo confirmed what Voyager had hinted. Io was astonishingly active. Infrared instruments detected hotspots scattered across the surface, glowing with heat from ongoing eruptions. Some were so bright they saturated the detectors, overwhelming their ability to measure. These hotspots shifted and changed over weeks and months, evidence that Io's surface was constantly being remade. In visible light, Galileo captured plumes rising above the horizon, great fountains of gas spreading into space. It also imaged fresh lava flows, dark streaks spreading across the plains, burying older deposits. The surface Voyager had shown was already different, altered by the passage of only a decade. One of the most remarkable discoveries was the persistence of Loki Patera, the enormous lava lake that Voyager had glimpsed but not fully understood. Galileo's instruments revealed its cyclical behavior, brightening and dimming as the crust of the lava lake overturned. This cycle, lasting months at a time, became a key to understanding how Io's volcanic systems work. Loki was not a temporary feature but a permanent furnace, releasing more heat than all of Earth's volcanoes combined. Galileo showed that Loki was, in many ways, the heartbeat of Io, a steady source of activity that had likely persisted for centuries. Another dramatic sight was the eruption of Pilon Patera in 1997. Galileo captured images of this eruption in progress, one of the most powerful volcanic events ever seen in the solar system. A vast plume rose into space, depositing a dark ring hundreds of kilometers across. Lava flows spread outward, covering thousands of square kilometers of surface. In infrared, the heat from Pilon was extraordinary, a furnace of molten rock glowing across the spectrum. To watch such an eruption unfold on another world was unprecedented, a moment when planetary science shifted from studying frozen landscapes to observing active geology in real time. Galileo also revealed the scale of Io's mountains, some rising more than twice as high as Everest. Images showed their fractured slopes, their towering cliffs, their evidence of landslides and collapse. These mountains were not part of ranges but stood alone, tilted blocks of crust uplifted by stress. The sheer size of them confirmed that Io's crust was strong, capable of supporting immense structures despite constant upheaval. Yet their fractured appearance also showed that nothing on Io was permanent. Mountains might rise, but they would eventually crumble, buried beneath flows or broken by stresses from below. One of the key contributions of Galileo was in connecting Io's volcanism to Jupiter's magnetic field. Instruments detected how Io's plumes released gas that became ionized, feeding the plasma torus that encircles Jupiter. They measured the electric currents linking Io to the planet, currents strong enough to generate auroras at Jupiter's poles. Galileo demonstrated beyond doubt that Io was not just shaped by Jupiter, but actively shaping its parent in return. The interaction was two-way. Jupiter's gravity fueled Io's fire, and Io's eruptions fueled Jupiter's light. Galileo also provided deeper insights into Io's atmosphere. It confirmed that the thin layer of sulfur dioxide waxed and waned with the cycle of day and night, collapsing at night and reforming in daylight. It showed how plumes thicken the atmosphere locally, creating temporary regions of denser gas. It also measured how the atmosphere interacted with Jupiter's magnetosphere, contributing particles to the plasma torus. In every way, Galileo revealed the atmosphere not as a passive veil but as an active participant in Io's cycle of restlessness. Perhaps the most striking impression from Galileo's observations was change. Every flyby revealed differences: new flows, new deposits, new plume rings, new mountains partially collapsed. Io was a world in constant motion, a surface that could not hold still long enough to preserve its past. Where Earth's landscapes change slowly, over centuries or millennia, Io's could shift in months. A plane imaged in one pass might be buried in lava by the next. A plume visible on one orbit might vanish by the next. This rapid pace of change made Io a world alive in a way that no other moon is. The data Galileo returned transformed our understanding of Io's interior. Models suggested that beneath the crust lay a layer of partially molten rock, perhaps a global magma ocean sustained by tidal heating. The constant flexing of Io's orbit churned this layer, generating heat that rose to the surface in eruptions. This explained the abundance of lava lakes, the persistence of plumes, and the scale of eruptions. It also highlighted Io as a laboratory for tidal heating, a process that may operate on other worlds, including Europa and exoplanets far beyond our solar system. For planetary scientists, Galileo's long watch over Io was invaluable. It confirmed that the discoveries of Voyager were not anomalies but part of a continuous story. Io was not briefly active but permanently restless, erupting without pause, reshaping itself in ways that could be tracked in real time. It showed that moons could be as dynamic as planets, that small bodies could host processes more extreme than anything on Earth. It also deepened our understanding of how moons interact with their parent planets, creating systems of energy and light far larger than themselves. For the public, Galileo's images of Io were unforgettable. The colours were surreal: reds, yellows, blacks, whites, all painted across the surface in shifting patterns. The plumes looked like fountains on a cosmic scale, silent umbrellas of gas spreading into space. The lava flows were vast, black rivers of molten rock cutting across plains. The mountains loomed jagged and immense, their shadows stretching across the surface. These images captured the imagination, showing a world that seemed almost too strange to be real, but was in fact very much alive. Galileo's mission ended in 2003, when the spacecraft was deliberately sent into Jupiter's atmosphere to avoid contaminating Europa, where an ocean beneath the ice might host conditions for life. But its legacy lives on, especially in what it taught us about Io. Voyager had revealed the existence of volcanism, but Galileo showed its persistence, its variety, its scale, and its consequences. It turned a shocking discovery into a sustained exploration, revealing Io as not just a curiosity, but as a key to understanding planetary processes across the solar system. To imagine Galileo's perspective is to picture a spacecraft looping again and again through the Jovian system, each time catching glimpses of Io, each time watching its surface change. Over years it saw eruptions rise and fade, flows spread and cool, mountains rise and collapse. It was a witness to a living world, a world that could never hold still, a world that challenged every assumption about moons. Through Galileo, Io's story became richer, deeper, more complex. It became not just the most volcanic world in the solar system, but one of the most important for understanding how worlds work. When Galileo showed us that Io was not just active but relentlessly active, the question of why became even more important. Voyager had revealed eruptions, Galileo had revealed their persistence, but the science behind them, the deeper explanation for all that heat and chaos, was still unfolding. To understand Io, scientists had to look not just at its surface but at its orbit, its interior, and its place in the Jovian system. The answer was not simple, but it revealed how invisible forces could create visible extremes, how a world's destiny could be written by the pull of gravity. At the core of Io's restlessness is tidal heating. The term itself sounds gentle, like the slow movement of tides across Earth's oceans, but on Io it is anything but gentle. Io orbits Jupiter at a distance of about 422,000 kilometres, locked in a resonance with Europa and Ganymede that keeps its orbit slightly elliptical. This means that Io is not always the same distance from Jupiter. As it moves closer, Jupiter's pull strengthens, stretching the Moon more intensely. As it moves farther, the pull weakens, allowing the Moon to relax slightly. The cycle repeats every orbit, flexing the Moon again and again like a ball of rubber squeezed in a giant hand. That flexing is not harmless. The rocks inside Io are not perfectly rigid. As they are stretched and compressed, they rub against one another, creating friction. That friction turns into heat, just as bending a paperclip back and forth warms the metal. But unlike a paperclip, it is enormous, and the energy involved is vast. The heating generated inside is enough to melt rock, creating reservoirs of magma that feed eruptions on the surface. The heat is not a small addition but a flood, driving more volcanic activity than all of Earth's volcanoes combined. The scale of the heating is difficult to comprehend. Scientists estimate that Io produces about 100 trillion watts of heat, most of it from tidal forces rather than radioactive decay, which powers much of Earth's internal heat. That amount of energy explains the lava lakes, the plumes that touch space, the mountains fractured and slumping under stress. It also explains why Io has no craters. The surface is constantly being repaved, covered in flows, deposits and frost. Tidal heating is not an occasional process. It is constant, as reliable as Io's orbit, as steady as Jupiter's pull. But the heat does not distribute evenly. Some regions of Io glow with intense activity, where hotspots cluster and plumes rise. Others are quieter, coated in sulfur frost and older flows. The variation comes from the complexity of Io's interior. Beneath the crust, the distribution of magma is uneven, pockets and channels forming in ways that focus eruptions in some places and not others. Galileo's data suggested the possibility of a global magma ocean, a layer of partially molten rock beneath the crust, churning constantly under tidal stress. If true, this would make Io unique, a world whose entire interior is dominated by molten heat. The chaos on Io's surface reflects this internal storm. Lava lakes overturn in cycles, plumes erupt without warning, flows spread across plains at incredible speeds. Nothing is permanent. Where Earth has landscapes that endure for millions of years, Io's features may last only months. The chaos is visible even in spacecraft images, where a region imaged once may look completely different a year later. It is geology in fast motion, a world that refuses to hold still, a surface that erases itself as quickly as it is drawn. For scientists, Io is a natural laboratory. By studying it, they can see tidal heating in action, a process that may shape many worlds. Europa, with its hidden ocean, is also heated by tides, though less violently. Enceladus around Saturn experiences tidal heating too, driving its icy geysers. Even exoplanets orbiting close to giant stars or other planets may experience tidal heating, perhaps making them volcanically active or sustaining subsurface oceans. Io shows us the extreme, the upper bound of what this process can do. It is the most chaotic example, but by studying it, we learn about a spectrum of possibilities across the universe. The science of Io's heat is also the science of balance. The resonance with Europa and Ganymede keeps its orbit eccentric, preventing it from settling into calmness. Without that resonance, the orbit would circularize, the heating would fade, and Io would quiet. But the dance of the three moons ensures that the cycle continues. It is a delicate but stable arrangement, one that has lasted for billions of years and will likely last for billions more. Io is trapped in that balance, unable to escape, destined to burn as long as the resonance holds. The chaos that results is not only geological but environmental. The atmosphere of Io, thin and fleeting, depends on volcanic eruptions to replenish it. Without the constant release of sulfur dioxide, the atmosphere would collapse entirely. The plasma torus around Jupiter depends on Io's eruptions too, fed by the gases escaping into space. Even Jupiter's auroras are shaped by Io's activity, their brightness varying with the intensity of the moon's eruptions. In this way, Io's heat fuels not only its own chaos, but the environment of an entire planetary system. The heat also explains Io's mountains, some rising taller than Everest. The stresses that create them come from the same tidal flexing that melts the interior. As the crust is pushed and pulled, blocks of rock are uplifted and tilted, forming jagged peaks. But those same stresses eventually break them down, causing landslides and collapse. The mountains of Io are monuments to stress, rising and falling as part of the same cycle that fuels eruptions and plumes. They are chaos in solid form, visible reminders of the forces within. For planetary scientists, one of the most intriguing aspects of Io is that it offers a glimpse into Earth's past. Billions of years ago, when Earth was young and hotter, ultramafic lavas may have erupted at similar temperatures to those seen on Io today. The processes shaping Io may echo those that once shaped Earth, before plate tectonics and oceans softened the planet's surface. In this sense, Io is not only a world of the present, but a window into the past, preserving conditions long vanished from our planet. But while Io teaches us about Earth, it also challenges us. The chaos of its surface, the speed of its changes, the violence of its eruptions, all push against our assumptions of stability and permanence. It reminds us that not all worlds are slow and steady. Some are fast, violent and unpredictable. Io is a reminder of extremes, of how much variety exists in planetary processes, of how the same forces that create calm oceans on one world can create burning lakes of lava on another. The science of Io's heat and chaos is therefore not only about Io itself, but about universality. It shows us how gravity can be a source of energy, how orbits can shape geology, how invisible forces can create visible phenomena. It connects the dots between worlds, linking moons and planets across the solar system and beyond. By studying Io, we learn not only about a fiery moon, but about the principles that govern countless other worlds, each with its own version of heat and chaos. To imagine Io's heat is to imagine a world where the ground is never still, where lakes of fire glow in alien colours, where plumes rise into space, where mountains crumble under stress. To imagine its chaos is to imagine a world where permanence does not exist, where every landscape is temporary, where every surface is waiting to be remade. To study it is to see the extremes of planetary science, the upper limits of what nature can create. When we look across the solar system, many moons seem frozen in time. Our own moon carries the scars of impacts billions of years old, preserved because nothing erases them. Callisto, orbiting Jupiter as well, is a graveyard of craters, its surface unchanged for eons. Even the icy shells of Europa and Enceladus, while dynamic in their own way, hold on to their histories, their surfaces marked by cracks and fractures that remain visible for long ages. Io is the exception. It does not preserve the past. It cannot hold still long enough to remember. Its surface is constantly buried, erased, painted over, reshaped, as though the moon itself refuses to rest. Io is, in every sense, a moon that could never sleep. The reason for Io's sleeplessness lies in its place in Jupiter's system. The constant pull of Jupiter's gravity, amplified by the tug of Europa and Ganymede, keeps Io in perpetual motion, orbiting with an eccentricity that forces its interior to flex endlessly. This flexing produces friction, and friction produces heat. The heat melts rock, creating magma, and the magma forces its way upward, breaking through the crust in eruptions that repaint the surface. The process never stops because the orbital resonance never ends. Io is caught in a loop, a cycle of heating and erupting without pause, without relief. On Earth, even the most active volcanoes have periods of quiet. They erupt, then fall silent for years or centuries, their slopes growing calm as vegetation returns. On Io, silence does not exist. At any given moment, dozens of volcanoes are active, their plumes rising into space, their flows spreading across the plains. Loki Patera, the giant lava lake, cycles endlessly between brightening and dimming, overturning its crust in a rhythm that may last for centuries. Pele erupts again and again, painting the surface with sulfur deposits. Pilon, Tavashtar, and countless others flare with violence, only to be replaced by new eruptions elsewhere. It is a ceaseless symphony of fire, a world where rest is not part of the vocabulary. The surface of Io bears witness to this sleeplessness. There are no old craters, no ancient scars. Every impact is quickly buried by lava or coated with sulfur frost. Mountains rise but eventually crumble, collapsing under stress or being engulfed by flows. Plains form but are soon covered in new deposits. Even the frost fields of sulfur dioxide sublimate and return in cycles of day and night, erasing themselves as they form. Nothing lasts, not even for centuries. To study Io is to study impermanence, a landscape that changes as quickly as we can observe it. From orbit, this restlessness is clear. Images taken months apart show new flows where none existed before, new rings of plume deposits, new patches of brightness or darkness. The changes are visible even from millions of kilometers away, proof that the moon never holds still. Where other worlds demand patience to see change, Io shows it readily, offering a moving picture instead of a still portrait. It is as if the moon itself is alive, shifting constantly, burning with energy that never allows it to stop. The sleeplessness of Io extends beyond its surface. Its atmosphere, thin and fragile, breathes in and out with the cycle of day and night. By day, sunlight warms the frost, releasing sulfur dioxide into gas that hovers briefly above the plains. By night, the gas collapses, freezing back into frost. The atmosphere disappears and reappears every cycle, as restless as the surface itself. It cannot hold steady. It cannot last. Even the air of Io refuses to sleep. This endless activity shapes not only the moon but its environment. The gases that escape from Io form the plasma torus around Jupiter, feeding the giant planet's magnetosphere with charged particles. The currents flowing between Io and Jupiter create auroras at the poles of the gas giant, glowing permanently in the sky of a world more than 1,000 times larger than the moon that fuels them. Io's restlessness is written across the entire Jovian system, a small body shaping phenomena on a massive scale. Even when we look at Jupiter itself, we are seeing the sleeplessness of Io, transformed into light and colour far from its source. For future explorers, Io's refusal to rest will be one of its greatest challenges. A spacecraft flying past must endure a radiation environment intensified by Io's contributions to the plasma torus. Any probe attempting to land would face unpredictable eruptions, flows that could overwhelm instruments, plumes that could coat equipment in frost. Even orbiting close to Io would be dangerous, the environment constantly shifting, the surface never reliable. The very energy that makes Io fascinating also makes it treacherous. A place where sleep is impossible, not only for the moon, but for those who would study it. And yet in this endless activity lies beauty. The glowing lava lakes, the soaring plumes, the painted plains of sulfur, the jagged mountains. All of it exists because Io cannot rest. If it were quiet, if it had cooled long ago like Callisto, it would be grey, cratered and silent. Another relic of the solar system's past. Instead, it burns with youth, its surface young and vivid, its processes ongoing. Its sleeplessness is what makes it unique, what makes it stand out among the moons of the outer solar system. It is not only the most volcanic world, but the most restless, a place that embodies change itself. For scientists, Io's sleeplessness is invaluable. It allows them to study volcanic processes in real time, to watch eruptions as they happen, to measure heat and change directly. It shows them how tidal heating works, how orbits and gravity can create energy, how small worlds can be shaped by the giants they orbit. It also teaches them about impermanence, about how surfaces evolve, about how planets and moons are not static but dynamic. By studying Io, they learn not only about a moon, but about the principles that govern worlds across the universe. For the imagination, Io's sleeplessness is compelling. To picture a world where fire never rests, where the ground is never still, where plumes rise into space without pause, is to picture something truly alien. It is to imagine a world that burns endlessly in silence, a world that embodies motion without sound, change without end. It is to imagine a place where even time feels different, because nothing is preserved, nothing is remembered, everything is erased and replaced in a constant cycle of renewal. This is why Io is often described as violent, as chaotic, as extreme, but it is also why it is beautiful. In its refusal to sleep, it creates landscapes of colour and light, plumes that touch space, auroras that glow on a giant planet. Its sleeplessness is destructive, but it is also creative, making Io not only a moon of fire, but a moon of wonder. It is a reminder that rest is not the only path, that some worlds live by never stopping, by burning constantly, by embracing change at every moment. As we reflect on Io's sleeplessness, we see how it connects to larger questions. What does it mean for a world to be alive? For Earth, life is tied to biology, to ecosystems and organisms. For Io, life is geological, a surface that moves, a crust that burns, a landscape that renews itself. It is alive not with creatures but with processes, not with cells but with magma. Its sleeplessness is its vitality, its refusal to fall into stillness, its proof of energy. In this way, Io expands our definition of what it means for a world to be alive, showing us that geology itself can be a form of life, a constant beating heart made not of blood but of fire. And as we carry this vision forward, as we imagine the moon that could never sleep, we are drawn naturally to the next thought. What can Io's sleeplessness teach us about Earth? What can its fire reveal about our own planet, about the processes that shaped it, about the role of volcanism in making Earth habitable? When we look at Io, the most volcanically active body in the solar system, it can seem at first to be utterly alien. A world painted in sulfur, scarred by lava lakes, and lit by plumes that rise hundreds of kilometers into space, appears far removed from the blue and green Earth we know. And yet, when scientists study Io, they find echoes of our own planet's story written across its restless surface. The violent sleeplessness of Io may seem extreme, but in its fire and chaos lie lessons that reach back into Earth's past, help us understand its present, and even guide our thinking about its future. The first and perhaps most profound lesson Io teaches us is about energy. Earth's internal heat comes from two main sources: the decay of radioactive elements within its mantle and core, and the residual energy left over from the planet's formation. That heat drives plate tectonics, powers volcanoes, and fuels the cycles that shape our planet. Io's heat, by contrast, comes primarily from tidal forces, from the constant flexing caused by Jupiter's gravity and the resonance of its neighbouring moons. The processes are different, but the result is the same: internal heat transformed into geological activity. By studying Io, we're reminded that energy can come from multiple sources, and that the way a world is heated can determine everything about its surface and atmosphere. This matters for understanding Earth because it highlights how fragile and specific our own balance is. Without sufficient internal heat, Earth would have cooled long ago, its volcanism fading, its tectonic plates grinding to a halt. the recycling of materials between mantle and crust would have stopped, leaving the planet geologically dead, like Mars or the Moon. Life as we know it depends on Earth's internal heat, which shapes continents, renews soils, and cycles gases into the atmosphere. Io shows us a world where heat is even more abundant, where volcanism is magnified to extremes, where the planet is remade constantly. By comparing the two, we see more clearly how important Earth's own, more measured heat is for maintaining conditions suitable for life. Io also teaches us about the importance of volcanism in shaping planetary environments. On Earth, volcanoes are often seen as destructive, their eruptions hazardous to people and ecosystems. But in a broader sense, volcanism is creative. It brings new materials from the interior to the surface. It builds land. It releases gases that help sustain the atmosphere. Billions of years ago, volcanic activity played a central role in forming Earth's early atmosphere, releasing water vapor, carbon dioxide, and other gases that created conditions for oceans and eventually life. Io, in its sleepless volcanism, offers a living model of such processes. It shows us volcanism not as an occasional event, but as a defining force, shaping an entire world. By observing Io's plumes and deposits, scientists gain insight into how volcanic gases interact with surfaces and atmospheres. The sulfur dioxide released on Io may be alien to us, but the principle is the same as on Earth. Gases escaping from the interior can change the air above and the landscape below. Io demonstrates the scale such processes can reach, with eruptions so vast they affect not only the Moon but the space around Jupiter. On Earth, volcanic eruptions affect climate, sometimes cooling the atmosphere for years by spreading particles high into the stratosphere. By comparing Earth's volcanic effects with Io's much larger ones, scientists learn about the limits of volcanic influence and about how different compositions and conditions shape outcomes. Another lesson Io offers lies in the chemistry of its lavas. On Earth today, most eruptions involve basaltic lava, molten rock with moderate temperatures and familiar properties. But billions of years ago, when Earth was hotter, ultramafic lavas rich in magnesium may have erupted at much higher temperatures, glowing white-hot and flowing more quickly across the land. Such lavas are thought to have played a role in shaping the early crust, in forming the continents, and in creating the environments where life eventually arose. Io still produces lavas at similar temperatures today, a living example of Earth's geological past. By studying Io's eruptions, scientists catch a glimpse of what Earth may have looked like in its infancy, a world of fire and molten seas, long before oceans and forests softened its face. Io also highlights the role of stress in shaping landscapes. Its towering mountains are not formed by the slow collision of tectonic plates as on Earth, but by the tilting and uplifting of crust under immense strain. These mountains, some taller than Everest, rise because Io's surface is constantly pushed and pulled by tidal forces. On Earth, stresses also shape mountains, though in different ways. By comparing the two, scientists better understand how crust responds to pressure, how rock can fracture, tilt, and uplift under different conditions. Io demonstrates one path, Earth another, but the physics of stress and strain applies to both. Perhaps one of the most important lessons Io offers is about impermanence. On Earth, landscapes can endure for millions of years. The Grand Canyon, the Himalayas, the Sahara, all have persisted long enough for human civilizations to rise and fall in their presence. Io, by contrast, erases its surface constantly. Plains, flows, mountains, and frost fields all vanish in cycles of days, years, or centuries at most. Nothing lasts. To study Io is to study change in fast motion, a world where permanence is an illusion. This helps scientists appreciate the rare stability of Earth's surface, the unusual fact that our planet allows memories to endure in stone. It also challenges us to imagine how life might evolve on a world where the surface never holds still, where nothing is preserved, where the ground is in constant motion. Io also teaches us humility in planetary science. Before Voyager, few suspected that a small moon could host such violent activity. It was assumed that volcanism required a large planet, radioactive heating, and plate tectonics. Io shattered those assumptions, showing that gravity alone, through resonance and tidal heating, could sustain immense activity. For Earth, this lesson is a reminder that the universe is broader than our models, that processes can operate in ways we do not expect. It encourages scientists to think creatively, to look for volcanism or heating in places they might not have predicted, including exoplanets orbiting close to their stars. In a more philosophical sense, Io also teaches us about the relationship between creation and destruction. Its volcanoes destroy landscapes, burying plains, erasing features, collapsing mountains. But they also create new surfaces, new plains, new deposits, painting the moon in vivid colours. This cycle is mirrored on Earth, where volcanic eruptions can devastate regions but also create fertile soils, new land, and long-term benefits. Life on Earth exists in part because of the gases and materials released by volcanoes over billions of years. Io shows us the same principle at work, magnified and made alien, but still recognisable. Creation and destruction are not opposites, but partners, working together to shape worlds. From a human perspective, Io also helps us appreciate Earth's balance. Our planet is active, but not overwhelmingly so. Volcanoes erupt, mountains rise, earthquakes occur, but between them there is calm. This balance allows stability for ecosystems and civilizations. Io has no such calm. Its sleeplessness would make life as we know it impossible. To see Io is to be reminded of Earth's rare gift, activity enough to sustain life, but not so much as to erase it. Io is a lesson in extremes, a reminder that not every balance is habitable, that Earth's middle ground is special. Io also challenges us to think about what we mean by a world being alive. We often equate life with biology, with cells and organisms. But Io shows us that geological life exists too, in a surface that moves, an interior that churns, a landscape that refuses to stay still. It broadens our perspective, reminding us that life is not the only way for a world to be active, that energy and change themselves can create vitality. For Earth, this lesson reinforces the idea that geology is not just background but a living system, one that interacts with biology, atmosphere, and oceans to sustain the planet we inhabit. And perhaps the greatest lesson Io gives us is perspective. For centuries, Earth was the measure of all worlds, the model against which everything else was compared. Io shows us that the universe is wider, stranger, more varied than that. It teaches us that moons can outshine planets in activity, that small bodies can drive phenomena on scales larger than themselves, that assumptions must be questioned. For Earth, this is a humbling realization, a reminder that our planet is one among many, each with its own story, each with its own extremes. To imagine standing on Earth, gazing through a telescope at the faint speck of Io, and knowing that it is erupting furiously even as you watch, is to feel that connection between worlds. Io teaches us not only about volcanism and geology, but about perspective, about how our place in the cosmos is part of a greater whole. Its sleeplessness mirrors our curiosity, its fire mirrors our search for energy, its impermanence mirrors the fleeting nature of time. In studying Io, we study ourselves, because the processes that shape it are part of the same universe that shaped Earth, the same laws that govern our own world. When we first set our gaze on Io through a telescope, it seemed no more than a point of light, one of Jupiter's many companions. Now, after decades of exploration and discovery, we know it as something far richer, a world of extremes, a moon defined by fire, silence, and restlessness. And as we close this long reflection, we are left not only with the facts of Io's geology, but with an impression, an image that lingers in the mind. It is an image of eruptions rising into space, of sulfur plains painted in alien colours, of mountains taller than Everest, of lava lakes glowing in darkness. But it is also an image of silence, of a world where all this violence unfolds without sound, without wind, without the familiar textures of Earth. There is something deeply striking about that silence. On Earth, fire is accompanied by noise, the crackle of flames, the roar of eruptions, the rush of air. On Io, there is none of that. A plume rising hundreds of kilometres into space does so without a whisper. A lava lake overturning its crust glows in silence. A landslide on the slope of a mountain crashes down without echo. The violence of Io is real, immense, overwhelming, and yet unfolds in complete quiet. That combination of fire and silence makes Io one of the most surreal places in the solar system. To picture it is to picture energy without sound, light without noise, destruction without roar. It is to imagine a world that burns eternally in stillness. That stillness paradoxically makes Io restful in its own way. Though the surface is constantly in motion, though eruptions never cease, the absence of atmosphere gives it a sense of calm. The black sky stretches unbroken. Jupiter looms above in silent majesty, and the colours of the surface glow softly in the sunlight. For all its activity, Io is not chaotic in the way Earth's volcanoes feel chaotic. It is orderly in its cycles, steady in its patterns, reliable in its restlessness. It erupts not in surprise, but in rhythm, its heat flowing outward in endless waves. This is perhaps the greatest paradox of Io, that a world so violent can also feel so serene when we picture it. In reflecting on Io, we're also reflecting on extremes. No other world combines such constant volcanism, such towering mountains, such vivid colours, such powerful influence on its parent planet. Io is small, barely larger than our moon, and yet it shapes Jupiter's magnetosphere, feeds its auroras, and alters the environment of a system hundreds of millions of kilometres wide. Its reach is vast, its presence undeniable. To think of a single moon-shaping phenomena on the scale of Jupiter is to appreciate the interconnectedness of the cosmos, the way small worlds and large ones are bound together in cycles of energy and motion. And yet, for all its grandeur, Io is also a reminder of fragility. Its atmosphere is thin and fleeting, vanishing every night and reforming by day. Its surface is impermanent, erasing itself again and again. Its mountains collapse, its flows spread and cool, its deposits fade. Nothing lasts, not even the most spectacular eruption. Io is a world of impermanence, a place where the only constant is change. That fragility mirrors our own sense of time, the way moments pass and are replaced, the way nothing holds forever. To reflect on Io is to reflect on the fleeting nature of existence, written in sulphur and fire across the surface of a distant moon. For us here on Earth, Io's story is a gift. It shows us what is possible when gravity and energy collide, when a small moon is caught in the grip of a giant planet. It expands our imagination, reminding us that worlds need not follow familiar patterns. It teaches us about energy, volcanism, stress, and impermanence. It reminds us that the universe is richer than our expectations, more varied than our models, more surprising than we dare to assume. Io is not only a moon, but a teacher, a fiery reminder that the cosmos is alive with processes beyond our daily experience, and perhaps most importantly, Io is a companion in thought. As we drift toward rest, picturing its glowing lakes and painted plains, we can let its fire become a kind of comfort. Its restlessness becomes a rhythm, steady and eternal. Its silence becomes soothing, a reminder that even the most violent processes can unfold in peace. To think of Io is to think of constancy within change, energy within stillness, motion within silence. It is to imagine a world burning forever, not in chaos but in rhythm, a heartbeat of fire that never stops. As we close our reflection, imagine yourself drifting in orbit above Io, looking down on its surface. Below, lava glows in alien colours, plumes rise like fountains into the blackness, mountains cast long shadows across sulphur plains. Above, Jupiter fills the sky, its bands and storms swirling in majestic calm, its auroras glowing faintly at the poles. Around you, silence stretches endlessly, a silence deeper than any found on Earth. You're watching a world that never rests, a world that cannot sleep, a world that embodies both violence and peace. You're watching Io, the most violent moon in the solar system, and yet in its fire and silence, you are finding rest. So let that image linger. Let the glow of Io's lakes warm the imagination. Let the silence of its eruptions ease the mind. Let the endless cycle of its surface, forever remade, become a reminder that change is natural, that impermanence is part of all things. Let Io, sleepless and fiery, become a source of calm, a companion in the night sky whose story is one of both restlessness and peace. And as you drift away, let the thought of this distant moon, burning in silence around a giant planet, carry you gently into rest. Thank you for spending this time together, exploring the story of Io, the most violent moon in our solar system. I hope the journey has left you calmer, more at ease, and perhaps just a little more curious about the wonders that fill the universe. If you've enjoyed drifting through these thoughts, and if you'd like more quiet explorations like this one, you can support the channel with a like or a subscription. It helps this little corner of calm science continue to grow. For now though, let the story fade into silence. Let the images of distant worlds become gentle background to your own rest. Breathe slowly, let your thoughts grow lighter, and allow yourself to drift away. The universe will still be waiting when you wake. Good night.